Princeton, New Jersey. April 18th. A nurse on the night shift hears a few words spoken in German, and then silence. By the time she reaches the bedside, Albert Einstein is gone. He was 76 years old. He died working. On the nightstand beside him sat 12 pages of equations. His latest attempt at a unified field theory. He never finished them. Within hours, without asking his family, the pathologist on duty removed Einstein's brain and took it home. The world would spend the next several days mourning a genius. Newspapers ran the same photograph, the wild hair, the kind eyes, the slight smile. World leaders released statements. Scientists called him irreplaceable. But here is the thing, almost none of those tributes mentioned. Einstein had spent the last 30 years of his career fighting a theory he helped create. He had written a letter that contributed to the most destructive weapon in human history, and spent the rest of his life trying to undo that. He had been married twice, been a distant father, and watched a woman who may have shaped his earliest thinking disappear from the historical record entirely. The icon was already in place before the body was cold. There are two kinds of famous. The first kind is the fame that comes from what a person actually did, the specific, documented, often complicated record of decisions, discoveries, failures and consequences that make up a real life. The second kind is the fame that replaces all of that. It smooths the edges. It selects the moments that confirm what the audience already wants to believe. It turns a person into a symbol, and a symbol is always easier to understand than a human being. Albert Einstein got both kinds, and for most of the century since his name became a household word, the second kind has almost completely buried the first. This documentary is built on the first kind. The account you are about to watch draws on decades of scholarly research into Einstein's published papers, his private correspondence, the collected volumes of his writings maintained by Princeton University Press, and the work of historians and philosophers of science who have spent careers separating what Einstein actually thought from what he has been credited or blamed for thinking. None of what follows is invented. Some of it will be unfamiliar. A few parts of it will be uncomfortable. That is not the point of telling it. But it is an unavoidable consequence of telling it honestly. Now, what is this story actually about? On the surface, it is the story of one of the most productive scientific careers in recorded history. A man born in the southwestern German city of Ulm in 1879 who, by the time he was 26 years old and working a civil service job at a patent office in Bern, had produced a body of work that would fundamentally alter how human beings understand light, time, space, energy, and the structure of the universe itself. A man who spent the following decade extending that work into a theory of gravity so ambitious and so mathematically demanding that it took him 8 years of near-constant effort to complete it. A man who was awarded the Nobel Prize in Physics, who became the most recognizable scientist on the planet, who was consulted by presidents and prime ministers, and who died in a Princeton hospital in the spring of 1955, still trying to write one more equation. That story is true. It is also incomplete, because running alongside that scientific career, sometimes in parallel, sometimes in direct collision with it, is another story entirely. It is the story of Einstein and the scientific establishment he both shaped and fought. It is the story of a man who helped ignite the quantum revolution and then turned against it, who debated Niels Bohr across 2 decades in what became the most consequential philosophical argument in the history of modern physics, a dispute that touched on whether nature itself, at its most fundamental level, operates according to rules that can ever be fully known, who watched the implications of his own most famous equation detonate over 2 Japanese cities and spent the remainder of his life reckoning with what that meant. It is also the story of Mileva Maric, the Serbian physicist who studied alongside Einstein in Zurich, bore his children, and whose precise contribution to his early work remains one of the most carefully avoided questions in mainstream accounts of his career. It is the story of the Nazi regime that drove him from his homeland and dismantled the very scientific community he had helped build. And it is the story of the United States government that celebrated him publicly and surveilled him privately, compiling a file on his politics that would eventually run to over 1,400 pages. These are not separate stories that happen to involve the same man. They are threads in a single fabric, and the only way to understand any one of them is to hold all of them at the same time. That is what this documentary attempts to do. The structure is deliberately braided. You will move between the scientific and the personal, between the public record and the private correspondence, because that is how Einstein's life actually moved. His physics was not sealed off from his politics, from his relationships, from his stubborn philosophical commitments. His decisions as a human being shaped the problems he chose to work on. The problems he chose to work on shaped the kind of human being he became. Separating those threads to make the story cleaner would mean telling a different story, one that is more comfortable and considerably less true. A word about how that braiding works in practice. There will be moments in this account where the science has to be explained with some care, not because the audience is assumed to be unfamiliar with Einstein's name, but because the specific arguments he made, and the specific arguments his opponents made in return, are not always accurately represented in popular accounts. The debate between Einstein and Bohr, for instance, is often reduced to a kind of shorthand. Einstein said, "God doesn't play dice." Bohr told him to stop telling God what to do, and quantum mechanics won. That version is not wrong exactly, but it leaves out almost everything that makes the debate worth understanding. When the science appears here, it will be explained in plain language. The goal is not to simplify it into something it is not, but to make it accessible without making it false. Ulm, Germany, in 1879, was a mid-sized industrial town on the Danube River, unremarkable by most measures except for its cathedral, the tallest in the world at the time, and a modest tradition of civic commerce. Hermann Einstein, Albert's father, ran an electrical engineering business with his brother Jakob. Pauline Einstein, Albert's mother, was by most accounts the more intellectually driven of the two parents. The family was Jewish, though not observant in any strict religious sense. They were bourgeois, settled, and by the standards of the German Jewish community of the era, relatively assimilated. Einstein was born on March 14th. His mother initially worried that his head was too large and misshapen. He was slow to speak. Family law held that he did not begin forming sentences until he was nearly 3 years old. Whether this later fed the mythology of the late blooming genius is difficult to say, but the mythology certainly found a use for it. The family moved to Munich shortly after Albert was born, where his father and uncle had opened a new electrical firm. It was in Munich that Einstein received his early schooling, and it was there at the Luitpold Gymnasium that the first recognizable patterns of his intellectual character began to appear. He excelled, by all surviving accounts, in mathematics and physics. He was less interested in subjects that required memorization without underlying principle. The gymnasium's emphasis on rote learning and strict authority made him deeply uncomfortable. He was, by most teacher assessments, not a difficult student in the disciplinary sense, but he was an independent one, which in that environment amounted to roughly the same thing. When he was 21 years old, a Jewish medical student named Max Talmud began visiting the Einstein household regularly for meals, a common practice of the time by which Jewish families supported students who could not afford to feed themselves adequately. Talmud was 12 years older than Albert and took an immediate interest in the boy's curiosity. Over the course of several years, he brought Einstein books, popular science texts, Kant's critique of pure reason, works on geometry. He introduced Einstein to the systematic idea that the universe operates according to principles that can be reasoned out rather than simply observed. That idea would become the foundation of everything Einstein later produced. In 1894, the family's electrical business failed, and Hermann and Pauline relocated to northern Italy, hoping to rebuild. Albert stayed behind in Munich to finish his schooling. Within months, he found the situation intolerable and left without graduating. Joining his parents in Pavia, he was 15 years old, stateless in the sense that he no longer had an established schooling path, and had made his first significant act of institutional non-compliance. The following year, he attempted the entrance examination for the Swiss Federal Polytechnical School in Zurich, what would later be renamed the Eidgenössische Technische Hochschule, or ETH. He failed, not across the board. His marks in mathematics and physics were strong, but his performance in French, botany and zoology was insufficient for admission. He was directed instead to a cantonal secondary school in Aarau, a small Swiss town roughly an hour from Zurich, where he spent a year completing the qualifications he needed. The time in Aarau was, by Einstein's own later account, among the most formative of his youth. The school's pedagogy was markedly different from the Luitpold Gymnasium, less authoritarian, more oriented toward visual and conceptual understanding over memorization. It was there, walking to school one morning, that Einstein first posed to himself a question he would not fully answer for another 10 years. What would it look like to ride alongside a beam of light? What would you see? The image stayed with him. In January 1896, before sitting the Aarau examinations, Einstein did something that would follow him for years in terms of how he was perceived by German authorities. He formally renounced his German citizenship. The primary reason was practical. He did not want to be called up for military service in the German army. The consequence was that he spent several years completely stateless, not a citizen of Germany, not yet a citizen of Switzerland, carrying no national passport at all. He would not receive Swiss citizenship until 1901. He passed his examinations at Aarau and enrolled at the ETH in Zurich in October 1896. He was 17 years old. Among his fellow students were two people who would prove consequential to his life in entirely different ways. The first was Marcel Grossmann, the son of a Swiss industrialist, an exceptionally gifted mathematician who took meticulous lecture notes and who seems to have recognized early on that Einstein's mind operated at a level that made conventional studying something of a mismatch. Grossmann would later secure Einstein his position at the patent office in Bern, effectively rescuing his early career from what had become a genuinely precarious situation, and would, years after that, provide the mathematical scaffolding without which the general theory of relativity could not have been built. The friendship between Einstein and Grossmann was not incidental to the history of physics. It was structural. The second person was Mileva Maric. Maric was Serbian, born in 1875 in Tito, in what is now northern Serbia. She was 4 years older than Einstein and had navigated a series of institutional barriers to reach Zurich at all. Women were not admitted to most European universities in the 1890s. The ETH was among the small number of institutions willing to admit female students to science programs, though the social and academic environment remained largely hostile to their presence. Maric had already studied physics at the University of Zurich before transferring to the ETH's Mathematics and Physics teaching diploma program. She was, by every account that survives, a serious and capable physicist. She and Einstein began as classmates. They became intellectual companions. Their letters, which survive in considerable number, show two people who discussed physics with genuine depth and mutual engagement. Einstein wrote to her in September 1900, describing his enthusiasm for Boltzmann's kinetic theory of gases, with the kind of excitement that is unmistakably real, rather than performed. She responded in kind. They read the same texts, argued over the same problems, and referred to their shared intellectual project in terms that were, at minimum, collaborative. What the letters do not resolve, and what remains one of the most carefully navigated questions in Einstein's scholarship, is exactly how much of what Einstein was developing in those years emerged from discussions with Maric versus from his own independent thinking. Einstein himself, in the early years of their relationship, referred at least once in correspondence to our work and our theory. Historians have debated the significance of that language for decades. Some argue it reflected genuine intellectual partnership. Others contend it was the language of romantic closeness rather than scientific co-authorship. The papers published in 1905 carry Einstein's name alone. What is not in dispute is that by 1901, their relationship had produced a pregnancy that both of them handled in conditions of considerable secrecy. Maric returned to her parents' home in Novi Sad to give birth. The child, a girl they called Liesel, was born in early 1902. Einstein never saw her. The subsequent fate of Liesel Einstein was unknown to scholars until the 1980s, when a cache of letters between Einstein and Maric came to light. The letters suggest the child was likely given up for adoption. She then disappears from the record entirely. No subsequent document in Einstein's archive mentions her again. Einstein, meanwhile, was in Bern. He had graduated from the ETH in 1900 with a teaching diploma in mathematics and physics, but had been unable to find an academic position. Several of his classmates received appointments or assistantships through the normal channels. Einstein did not. He applied repeatedly and was turned down. The reasons are not entirely clear. Some scholars point to a difficult relationship with one of his professors, Heinrich Weber, who had found Einstein's independent attitude a persistent irritant. Whatever the cause, the result was that the young man who would, within 5 years, produce one of the most remarkable sequences of scientific papers in the history of physics, spent the intervening period working as a substitute teacher and private tutor in small Swiss towns, scraping for income and waiting. Before the papers of 1905 are examined, something needs to be addressed directly because it sits underneath everything that follows, and skipping past it would mean accepting a version of this story that the evidence does not fully support. Mileva Maric has been one of the most contested figures in the history of modern science. Not because her life was obscure, the basic facts are well documented, but because the question of what she contributed to Einstein's early work has been handled by historians, biographers, and institutions alike, with a degree of evasiveness that itself tells a story. She was, to be clear, not a peripheral figure in Einstein's life during the years that mattered most scientifically. She was his closest intellectual companion from 1896 through at least 1905, and arguably beyond. She studied the same curriculum. She read the same texts. She sat in the same lectures at the ETH delivered by professors who included Heinrich Weber, whose courses on Maxwell's electromagnetic theory were among the most rigorous available anywhere in Europe at the time. She was not a bystander to Einstein's intellectual development during those years. She was present at its centre. The question that has divided scholars is a more specific one. Was she a contributor to the content of what Einstein published, or was she a companion to the process? Someone whose presence, whose conversation, and whose own thinking created the conditions in which Einstein's ideas could develop, without directly shaping the ideas themselves? The honest answer is that we do not know with certainty, and the reason we do not know is partly a function of how the historical record was assembled, and partly a function of how quickly that record moved to centre Einstein and Mileva Maric once the marriage ended and the fame began. What the surviving letters do establish is this: Einstein and Maric corresponded extensively between 1897 and their marriage in 1903, and those letters show a relationship in which physics was not background conversation but central content. Einstein describes problems he is working on. He asks for her opinion. He reports her responses as mattering to him. In September 1900, he writes to her about Boltzmann's work with genuine intellectual enthusiasm and signs his letter in terms that suggest a shared project rather than a solo one. Historians who have studied the letters in depth, among them John Stachel, one of the founding editors of the collected papers of Albert Einstein, have generally concluded that the letters show a deep intellectual companionship, but do not constitute clear evidence of co-authorship in the technical sense. Others disagree. The physicist and historian Evan Harris Walker argued in the 1980s that Maric's mathematical abilities were central to the development of the special relativity paper. The biographer Desanka Trbojevic Guric, writing in Serbian and later translated, advanced the case for Maric as a genuine collaborator whose contribution was systematically erased. These arguments have not been accepted as definitive by the mainstream of Einstein scholarship, but they have not been fully refuted either. They occupy a space of genuine uncertainty that the field has not always been comfortable acknowledging. What makes the question harder to resolve is the absence of Maric's own scientific writings from this period. She attempted the final diploma examination at the ETH twice, in 1900 and again in 1901, and failed both times. The reasons for those failures are not entirely clear. Her grades in the earlier parts of the programme were adequate. Some historians have suggested that the circumstances of her first pregnancy, which overlapped with her examination preparation, were a significant factor. Others have pointed to the broader pattern of institutional hostility toward women in science at the time as context, if not explanation. What is certain is that after the second failed examination, Maric did not pursue an independent scientific career. She married Einstein, moved to Bern, and took up the domestic arrangements of their shared life, while Einstein continued working at the patent office. The domestic arrangements are worth being specific about, because they bear directly on the question of her intellectual life after 1903. The Bern apartment was small. Hans Albert was born in 1904, requiring the kind of constant attention that in that era and in that household fell almost entirely to the mother. Einstein, by his own account and by the accounts of those who knew the family, was not a particularly involved domestic presence. He worked at the patent office during the day and used his evenings and weekends for his own theoretical work. Maric managed the household. Whether she also contributed to that theoretical work during those years, whether the conversations continued, whether she checked mathematics, whether she read drafts, is not documented with the specificity that would settle the question. What is documented is that Einstein, in a letter to his friend Conrad Habicht, written in the spring of 1905, describes 4 papers he is working on and refers, at one point, in a playful, but not obviously metaphorical way, to his wife as someone involved in the work on the electrodynamics paper. The reference is brief and has been interpreted in different directions by different scholars. it has not been resolved. The 1905 papers were published under Einstein's name alone. This was standard practice for the time, and it does not by itself establish that no collaboration occurred. What it establishes is that the record, as it entered the scientific literature, carried one name. The marriage itself deteriorated in the years following 1905. Einstein's career accelerated rapidly after the papers attracted attention. He received his first academic appointment in 1909, moved through a series of increasingly prestigious positions, and by 1913 had been offered a research professorship in Berlin, the pinnacle of the German scientific establishment, with no teaching obligations and a salary that reflected his standing. Maric followed him to Berlin in the spring of 1914 with their two sons, Hans Albert and Eduard, who had been born in 1910. She left within months. The marriage had been under strain for years. Einstein's letters from the Berlin period suggest a man who had emotionally withdrawn from the relationship considerably earlier, and who was, by the time the family arrived in Berlin, already deeply involved with his cousin Elsa Löwenthal, whom he would eventually marry. Maric returned to Zurich with the boys. The formal separation became permanent. The divorce was finalised in February 1919. The divorce settlement contained a clause that has attracted attention ever since it became widely known. Einstein, in negotiating the terms, agreed that if he were ever awarded the Nobel Prize, the monetary value of that prize would go to Maric. This was not a trivial concession. The Nobel Prize in Physics carried a cash award that represented many years of a professor's salary. Einstein made the commitment before he had won it, apparently in confident anticipation that he would. He received the prize in 1922, awarded for 1921. The money went to Maric, as agreed, and she used it primarily to purchase properties in Zurich that provided income for herself and the children. The gesture has been read in different ways. Some have seen it as evidence that Einstein felt a genuine debt to Maric, financial or otherwise. Others have interpreted it as a practical negotiating move by a man who knew the prize was likely and wanted to secure Maric's agreement to the divorce terms. The letters do not resolve which reading is correct. Both may be partially true. What happened to Maric after the divorce is a story that does not end well, and it is worth tracing briefly because it illustrates something about the specific costs that the structure of their arrangement and Einstein's choices within that arrangement carried for her rather than for him. The third floor of the Swiss Federal Patent Office in Bern was not, by any obvious measure, a place where the foundations of modern physics were likely to be rebuilt. The work was methodical and procedural. Applications came in describing mechanical devices, electrical systems, electromagnetic apparatuses. Einstein's job was to read each one carefully, assess the internal logic of its claims, identify whether those claims were coherent and whether they overlapped with existing patents, and write a clear evaluation. He was, by the assessments of his supervisors, good at this. He was promoted in 1904 from technical expert, third class, to technical expert, second class. But the evaluative habit that made him effective at patent work, the instinct to strip a claimed mechanism down to its underlying assumptions and ask whether those assumptions actually held, was the same habit he was applying, in the hours that were his own, to the foundations of physics. The Patent Office trained him, in a sense, to distrust stated premises, to ask not what a system claimed to do, but what it actually had to be true for the claim to be valid. That disposition runs through everything he produced in 1905. 4 papers, published between March and September in the Annalen der Physik, then the most prestigious physics journal in the German-speaking world, edited at the time by Max Planck and Wilhelm Wien. Each paper addresses a different problem. Each one is, by any reasonable measure, a career-defining contribution. That all four appeared within the span of roughly 6 months, from a man working a full-time civil service job, without access to a university laboratory, without academic colleagues in the immediate sense, and without any formal position in the scientific establishment, remains one of the most singular episodes in the history of science. The comparison to Newton's plague, years of 1665 and 1666, when Newton, similarly isolated at Woolsthorpe during the Great Plague's closure of Cambridge, developed calculus, the theory of colours, and the first outlines of universal gravitation, is one that historians reach for, and that Einstein himself would have recognised. It is not an idle comparison. In both cases, isolation from the normal institutional pressures of academic life appears to have been a condition that enabled rather than hindered the work. Neither man was distracted by the expectations of colleagues, the demands of teaching, or the social weight of existing consensus. The first paper, submitted in March, is the one Einstein himself considered the most genuinely revolutionary of the four. It concerns the nature of light. For roughly a century before 1905, the wave theory of light had been the settled framework of physics. James Clerk Maxwell's electromagnetic theory, confirmed experimentally by Heinrich Hertz in the late 1880s, described light as a wave propagating through space, a disturbance in the electromagnetic field. The evidence for this was strong. Interference and diffraction phenomena observable in any laboratory made sense only if light was a wave. The corpuscular theory, the idea that light was made of particles, had been largely abandoned since the early 19th century. Einstein looked at this settled consensus and found a crack. The crack was in the problem of black body radiation, the question of how a heated object distributes energy across the frequencies of light it emits. Planck had derived a formula in 1900 that matched the experimental data perfectly, but Einstein, examining Planck's derivation carefully, identified something Planck himself had not fully confronted. The formula only worked if you assumed, at some level, that energy in the radiation field was not continuous, but came in discrete packets. Planck had introduced this discreteness as what he called an act of desperation, a mathematical device to make the formula work, not a physical claim about how radiation actually behaved. Einstein made it a physical claim. In the March paper, he argued that under certain conditions, specifically at high frequencies and low radiation densities, light behaves not as a continuous wave, but as if it consists of discrete localized packets of energy, each with a magnitude proportional to its frequency. He called these packets light quanta. The proportionality constant connecting energy and frequency was Planck's own constant, which Einstein now elevated from a mathematical convenience to a fundamental feature of nature. This was, as Einstein recognized explicitly in a letter to Conrad Habicht, that spring the only one of his 4 papers that he considered truly radical. The others, he suggested in the same letter, were significant, but operated within or close to existing frameworks. The light quantum paper attacked a framework. It said that the accepted description of light, the continuous electromagnetic wave, was incomplete. That under the right conditions, light had a granular, particle-like character that the wave theory could not account for. The reception was sceptical, and the scepticism was not unreasonable. The wave theory had enormous experimental support. Even Max Planck, whose own formula Einstein was interpreting, rejected the light quantum hypothesis for years. In a 1914 letter recommending Einstein for membership in the Prussian Academy of Sciences, one of the most prestigious honours available to a German physicist, Planck wrote that Einstein had sometimes, quote, missed the target in his speculations, and cited the light quantum hypothesis as the primary example of this. That such a statement appeared in a letter of recommendation from one of the most eminent physicists in Europe tells you something about how the hypothesis was regarded by the establishment at the time. The second paper of 1905, submitted in May, addresses Brownian motion, the phenomenon first observed by the British botanist Robert Brown in 1827, in which small particles suspended in a liquid undergo a continuous, irregular, zigzagging movement that had never been satisfactorily explained. Einstein had not, at the time of writing, read a significant amount of the existing literature on the subject, a consequence of his limited access to university libraries. He was, in a sense, reasoning from first principles about what statistical mechanics required. His argument was this: if matter is composed of atoms and molecules in constant thermal motion, then a particle suspended in a liquid is being struck continuously on all sides by the molecules of that liquid. On average, the impacts balance. But statistical mechanics predicts that the impacts will not be perfectly balanced at every moment. There will be fluctuations, and those fluctuations should produce the observable random motion that Brown had seen under his microscope. Einstein calculated the mean square displacement a suspended particle should undergo over a given time interval and derived a formula that connected this observable displacement to Avogadro's number, the number of atoms in a mole of a substance. This was significant for two reasons. First, it provided a way to actually test the molecular theory of heat by watching particles under a microscope, by making the invisible effects of atomic motion visible at a scale accessible to experiment. Second, and more broadly, it demonstrated that classical thermodynamics, which dealt only with average values of macroscopic quantities, was not the whole story. Fluctuations from those averages were real, measurable, and theoretically significant. The experiments that confirmed Einstein's predictions were conducted in Paris in 1908 by Jean Perrin, whose measurements of suspended particles matched Einstein's theoretical formula with considerable precision. The former skeptics of atomism, the camp that had argued with some philosophical justification that atoms were theoretical conveniences rather than physical realities, largely abandoned their position after Perrin's results were published. Wilhelm Ostwald, a Nobel Prize-winning chemist who had been one of the most prominent critics of atomism, publicly reversed his view. The third paper, received by the Annalen der Physik on June 30th, is the one most people mean when they say special relativity. Its formal title was On the Electrodynamics of Moving Bodies. Its starting point was a tension that had been building in physics for decades, and that everyone recognised but no one had resolved cleanly. The laws of mechanics, as formulated by Newton, and the laws of electromagnetism, as formulated by Maxwell, were not fully compatible with each other. Specifically, Maxwell's equations predicted that light travels at a fixed speed, a specific numerical value, the same regardless of the motion of the source or the observer. Newtonian mechanics said that speeds should add and subtract in the ordinary way. You could not have both without contradiction. Einstein resolved the contradiction by accepting Maxwell's result as a postulate. The speed of light is constant for all observers in uniform motion, and then following the consequences wherever they led. What they led to was a systematic revision of the Newtonian concepts of space and time, absolute time, the idea that there is a single universal clock that runs at the same rate for all observers everywhere. Had to go. Absolute simultaneity, the idea that two events either happen at the same time or they do not in a way that all observers agree on, had to go with it. What replaced them were relations between space and time measurements that depended on the relative motion of observers, governed by transformations that Hendrik Lorentz and Henri Poincaré had written down mathematically but had not interpreted in the way Einstein now interpreted them. What made Einstein's treatment different from Lorentz's and Poincaré's was not the mathematics, which overlapped considerably, but the physical interpretation. Einstein was not patching the existing framework, he was replacing its foundations. He was saying that space and time measurements are not fixed features of reality that observers access with varying degrees of accuracy. They are quantities that are genuinely different for observers in different states of motion, and this is not a measurement problem, but a physical fact. The fourth paper, submitted in September, was a direct consequence of the third. It derived what is now the most famous equation in the history of physics, the equivalence of energy and mass. If the equations of special relativity were correct, Einstein showed, then a body that emits energy in the form of radiation must decrease in mass by an amount equal to that energy divided by the square of the speed of light. The relationship between energy and mass, in other words, was not a coincidence or an approximation. It was exact and universal. A given quantity of mass, completely converted to energy, would release an amount of energy equal to that mass multiplied by the square of the speed of light, a number of almost incomprehensible magnitude. Einstein, in September 1905, did not discuss weapons or bombs. He was describing a theoretical consequence of the equations of special relativity. The implications of that consequence for what could in principle be done with concentrated mass took several more decades, and the contributions of many other physicists to become the thing that would haunt him for the rest of his life. In 1905, it was a 4-page addendum to a paper about electrodynamics. To understand why Einstein eventually turned against quantum mechanics, you first have to understand what he believed he was doing when he helped create it, because he did not think he was founding a new framework that would replace classical physics. He thought he was identifying a problem, a deep structural crack in the existing foundations that a better theory would eventually repair. The quantum, in Einstein's mind, was a symptom. It was pointing at something real that the existing tools of physics could not yet describe. It was not in itself the answer. That distinction matters enormously for everything that follows. Max Planck introduced the quantum concept in December 1900 in a lecture to the German Physical Society in Berlin. He had been working for several years on the problem of blackbody radiation, the question of how a heated object distributes energy across the frequencies of electromagnetic radiation it emits. The experimental data on this distribution had been accumulating for years at the Physical Technological Imperial Institute in Berlin, where teams of experimentalists had constructed increasingly precise approximations of the theoretical black body and measured its radiation spectrum with growing accuracy. The theoretical side of the problem was more troubled. Two partial formulas existed. Wilhelm Wien's formula, derived in 1894, matched the experimental data well at high frequencies, but broke down at lower ones. The formula derived by Lord Rayleigh and later corrected by James Jeans worked at low frequencies, but led, when extended to high frequencies, to a result of complete absurdity. The total energy in the radiation field would be infinite. An infinitely energetic heated object is not a prediction any theory can survive. Planck's approach was to find a formula that bridged the two regimes, one that matched Wien's law at high frequencies and Rayleigh's at low ones. and that remained finite across the entire spectrum. He succeeded in finding such a formula in October 1900, essentially by interpolation, constructing an expression that fit the experimental data across the full range. But having a formula and understanding it are different things. Planck then faced the task of deriving his formula from physical principles, of finding a theoretical argument that would explain why it worked. To do this, he turned to the statistical methods of Ludwig Boltzmann, specifically Boltzmann's relationship between the entropy of a thermodynamic state and the probability of that state, the connection that would later appear carved on Boltzmann's tombstone in Vienna in its mathematical form. Planck followed Boltzmann's combinatorial method of counting the number of distinct ways energy could be distributed among a set of oscillators, but to make the counting work, to get a finite, well-defined number of configurations, he found he had to treat the energy of each oscillator not as a continuous variable, but as made up of discrete, indivisible units. Each unit had a magnitude proportional to the frequency of the oscillator, with a tiny proportionality constant that Planck introduced into physics for the first time. That constant now bears his name. Planck's own interpretation of this step was conservative, to the point of being contradictory. He regarded the energy elements as a mathematical device, a computational fiction necessary to make the counting procedure work, rather than a physical claim about how energy actually behaved. He believed, and continued to believe for several more years, that a more rigorous derivation would eventually eliminate the need for discrete energy elements and recover a fully continuous picture. He was, in the words of one historian of physics, a highly conservative revolutionary, someone whose mathematical result implied a radical departure from classical physics that its own author refused to accept. Einstein accepted it, and then he went further. The 1906 paper in which Einstein examined Planck's derivation critically is, by the assessment of the historian Thomas Kuhn, the moment at which the quantum revolution truly began, more so than Planck's original paper. What Einstein showed was that Planck's derivation, examined carefully, was internally inconsistent. Planck had started from classical electrodynamics and classical statistical mechanics, both of which implied continuous energy, and had then, midway through the argument, introduced discrete energy elements without any justification from those classical foundations. The formula worked, Einstein pointed out, precisely because Planck had smuggled in a non-classical assumption while claiming to be working within classical theory. This was not a minor criticism. It meant that Planck's formula could not be understood as a modification or refinement of classical physics. It required a genuine break. The discreteness of energy was not a computational convenience. It was a physical fact that any adequate theory of radiation would have to take seriously from the beginning. Einstein had taken it seriously from his very first paper on the subject, in March 1905, where he argued that radiation at high frequencies behaved as if it consisted of discrete energy packets. But the 1906 paper sharpened the claim considerably. It was no longer just a heuristic analogy or a useful way of thinking about the photoelectric effect. It was a demonstration that the entire framework of classical physics, mechanics, and electrodynamics together could not account for what Planck's formula described. Something fundamentally new was required. What Einstein then did with this recognition over the following 2 decades was build on it relentlessly, in directions that extended the quantum hypothesis far beyond radiation into the theory of matter itself. The 1907 paper on the specific heats of solids applied the same quantum restriction to the vibrational motions of atoms in solid materials, explaining anomalies in the measured heat capacities of certain substances, anomalies that classical statistical mechanics had been unable to account for, and that figures like Lord Kelvin had identified as among the deepest unsolved problems in physics. Einstein's quantum treatment predicted that the specific heat of a solid would decrease towards zero as temperature approached absolute zero, in agreement with what was being found experimentally and with Walter Nernst's independently proposed third law of thermodynamics. The 1909 Salzburg Address, delivered to the annual meeting of the German Physical Society, went further still. Einstein presented what he called a Brownian mirror argument, a thought experiment involving a small mirror suspended in a cavity filled with blackbody radiation, subject simultaneously to the random buffeting of gas molecules and to the fluctuating pressure of the radiation field. His fluctuation analysis of the radiation pressure on this mirror produced a result with two distinct terms. One term corresponded to the behaviour expected from a wave theory of light. The other corresponded to the behaviour expected from a particle theory. Both were required to describe the full blackbody spectrum. Neither alone was sufficient. This was the first explicit statement in physics of what would later be called wave-particle duality. The recognition that light was neither purely a wave nor purely a particle, but something that exhibited both kinds of behaviour depending on the circumstances of observation. Einstein did not present this as a philosophical puzzle or a paradox to be lived with. He presented it as evidence that existing theory was incomplete and that a future theory of light would have to be, in his own words, a kind of merger of the wave and particle pictures. He did not know what that theory would look like, but he was confident that it would be a unified deterministic description of nature rather than a permanently dualistic one. That confidence in the possibility of a unified, causally complete theory of radiation and matter was precisely what brought him into collision with the direction quantum mechanics took after 1925. But before that collision, there were further contributions to what historians call the old quantum theory that deserve attention, because they illustrate how deeply Einstein's fingerprints are embedded in the very framework he later opposed. In 1916 and 1917, Einstein returned to the problem of blackbody radiation with a derivation that was, for the first time, genuinely quantum theoretical rather than a hybrid of classical and quantum reasoning, working with the Bohr model of the atom, which had been published in 1913 and which described electrons occupying discrete energy levels within the atom and emitting or absorbing radiation only when jumping between those levels. Einstein constructed a statistical account of how a gas of atoms in thermal equilibrium with a radiation field would maintain that equilibrium through elementary processes of emission and absorption. The derivation introduced a distinction that proved foundational. Einstein identified two different types of emission. The first he called spontaneous emission, the process by which an excited atom drops to a lower energy state and releases a quantum of radiation without any apparent external cause, analogous to the spontaneous decay of a radioactive nucleus. The second he called stimulated emission, a process in which an atom in an excited state is induced to emit radiation by the presence of radiation already existing in the surrounding field at the same frequency. The emitted radiation in stimulated emission is coherent with the inducing radiation. It has the same phase, frequency, and direction. Planck's radiation law followed from the statistical balancing of these processes at thermal equilibrium, and for the first time it followed from a derivation that did not require inconsistent classical assumptions. The derivation was clean, rigorous, and self-contained within a quantum framework. The concept of stimulated emission remained largely theoretical for nearly 4 decades. In the 1950s, it became the operating principle of the maser and then the laser, technologies whose applications now range from surgical instruments to fibre optic communications to the barcode scanners in every supermarket on the planet. Einstein did not foresee any of this in 1916. He was solving a theoretical problem about the interaction of radiation and matter. The applications followed from the physics, as they tend to do, at a delay measured in decades. On January the 7th, 1907, Einstein recorded in his notes what he would later describe as the most fortunate thought of his life. It was not an equation, it was an image. A man falling freely from a rooftop, falling, not thrown, simply released, would not feel his own weight. In the instant of free fall, gravity would be, from that man's own perspective, absent. He would be, in a precise physical sense, weightless. This was not an observation about danger or misfortune. It was a recognition that the experience of gravity and the experience of acceleration were, under certain conditions, physically indistinguishable. An observer sealed inside a windowless box who felt a steady downward pull could not determine, from inside the box alone, whether that pull was caused by a gravitational field or by the box being accelerated upward through empty space. The two situations produced identical physical effects. That equivalence between gravitational force and inertial force due to acceleration was what Einstein immediately recognized as a principle, and it became the foundational heuristic from which the general theory of relativity would eventually emerge. The path from that insight in 1907 to the completed field equations of November 1915 was 8 years long, and it was not a straight line. It was a path marked by false starts, mathematical detours, philosophical commitments that turned out to be both essential and occasionally misleading, a near miss with another scientist working toward the same destination, and a level of sustained intellectual effort that Einstein himself later described in terms that suggested something close to physical exhaustion. Understanding why the path was so difficult requires being clear about what Einstein was attempting. Special relativity, completed in 1905, described the physics of observers moving at constant velocities relative to one another, what physicists call inertial frames. It said nothing about observers who were accelerating. Gravity, however, produces acceleration. An object falling towards the Earth is accelerating. The Moon in its orbit is continuously accelerating toward the Earth. Any adequate theory of gravity would have to deal with accelerating frames of reference, and special relativity, as Einstein had constructed it, was not equipped to do this. The principle of equivalence, the recognition that gravitational and inertial effects are locally indistinguishable, opened a path forward. If an accelerating frame and a gravitational field were physically equivalent, then the behaviour of light and matter in a gravitational field could in principle be deduced by analysing what happens in an accelerating frame. And what happens to light in an accelerating frame, Einstein realised quite quickly, is that it bends. If a beam of light enters a windowless accelerating box horizontally, it will appear to curve downward relative to the box's interior, because the box is moving upward while the light travels across. By the equivalence principle, this meant that light should also bend in a gravitational field, that a beam of starlight passing close to the surface of the sun would be deflected by the sun's gravity. Einstein calculated this deflection in 1911 and published the result. The calculation was based on the equivalence principle alone, without the full general theory, and it gave a value for the deflection that was, as it would later turn out, exactly half the correct answer. The error was not a mathematical mistake. It was a consequence of working with an incomplete theory. The full general theory, when it was eventually completed, doubled the predicted deflection. And that doubled value was what the 1919 solar eclipse expedition confirmed. But in 1911, Einstein did not yet have the full theory. He had a principle and a direction. What he did not yet have was the mathematics. This is where Marcel Grossmann re-enters the story. Grossmann, Einstein's old classmate from the ETH, the man whose meticulous lecture notes had helped Einstein pass examinations he had not adequately prepared for, and whose father's recommendation had secured the patent office position, was by 1912 a professor of mathematics at the ETH in Zurich, where Einstein had returned as a professor of theoretical physics. Einstein went to Grossmann with a specific request. He needed a mathematical framework capable of describing curved spaces, one that would allow the equations of physics to take the same form regardless of which coordinate system an observer used to describe them. He needed, in short, a geometry of the kind that Bernhard Riemann had developed in the 1850s for purely mathematical purposes, and a calculus, the absolute differential calculus, also called tensor calculus, that had been developed by Gregorio Ricci Cubastro and Tullio Levi Civita at the turn of the century. Grossmann knew this mathematics. Einstein did not. The collaboration that followed was one of the most productive interdisciplinary partnerships in the history of physics, and also one of the most asymmetric. Grossmann provided the mathematical tools. Einstein provided the physical intuition about what those tools needed to accomplish. Together in 1913, they published what they called the Entwurf, German for outline or draft, a preliminary version of a relativistic theory of gravity that had many of the right structural features but contained errors in the gravitational field equations that Einstein would not fully identify and correct for another 2 years. The Entwurf period was one of the most difficult of Einstein's career. He believed for a time, incorrectly, that the field equations of a generally covariant theory, a theory whose equations maintained the same form under arbitrary changes of coordinates, could not be derived from physical principles alone. This led him to adopt a restricted form of covariance that he later recognized as a mistake. The philosophical commitment to what he called Mach's principle, the idea that the inertial properties of matter are determined by the distribution of all other matter in the universe, rather than by an absolute space, guided him in some directions that proved productive and others that proved dead ends. What kept him oriented through all of these difficulties was the principle of equivalence and a growing conviction that the geometry of space-time itself, the curvature of the four-dimensional continuum in which events occur, was the physical expression of gravity. Gravity, in Einstein's emerging picture, was not a force acting across space in the Newtonian sense. It was the curvature of space-time produced by the presence of mass and energy, and what we experience as gravitational attraction is simply the tendency of objects to follow the straightest possible paths, geodesics, through that curved geometry. A planet orbiting the Sun is not being pulled by a force. It is following the straightest available path through the curved spacetime that the Sun's mass has produced around it. This was a conceptual shift of the most radical kind, a replacement of Newton's gravitational force with a geometric description of space-time itself. And it required field equations that would specify exactly how the distribution of mass and energy in a region of space-time determined the curvature of that region. Finding those equations in their correct, generally covariant form was what took 8 years. The final sprint came in November 1915, and it came under conditions of significant pressure. David Hilbert, the most eminent mathematician in Germany, and one of the most eminent in the world, had attended a series of lectures Einstein gave in Göttingen in the summer of 1915 on the current state of his gravitational theory. Hilbert, with the mathematician's instinct for formalization, had begun working on the problem himself, approaching it from the side of mathematical elegance and a theory of matter due to Gustav Mie. By the autumn of 1915, both Einstein and Hilbert were racing, largely independently, toward the correct field equations. Einstein presented 4 papers to the Berlin Academy on consecutive Thursdays in November. The third, on November 18th, contained a result that stopped him. Using a preliminary version of the new field equations, he calculated the anomalous precession of the perihelion of Mercury. The slow, centuries-long rotation of the point of Mercury's closest approach to the Sun, which Newtonian gravity had never been able to fully account for. The observed discrepancy had been known for decades and had resisted every attempted explanation. Einstein's new equations gave a value that matched the observations exactly. He later said that his heart trembled when he saw the result. For days afterward, he was too excited to work normally. The fourth paper, on November 25th, presented the gravitational field equations in their final, fully generally covariant form. Hilbert submitted a paper containing equivalent equations 5 days earlier, on November 20th. Though subsequent historical analysis has established that Hilbert's submission was revised after the submission date, and that the version he originally submitted did not contain the explicit equations in the form they later appeared, the precise question of priority has been debated by historians for decades and has not been resolved to everyone's satisfaction. What is not disputed is that Einstein and Hilbert arrived at the same mathematical structure through entirely different routes. Einstein from physical principles, Hilbert from mathematical ones, and that the physical interpretation, the conceptual framework that made the equations a theory of gravity rather than a set of field equations, belonged to Einstein. The canonical presentation of the complete theory appeared in March 1916 in the Annalen der Physik, the same journal that had published the 1905 papers under the title The Foundation of the General Theory of Relativity. It was by any measure one of the most complete and self-contained theoretical achievements in the history of physics. A theory that began from 2 principles, the equivalence principle and the principle of general covariance, and derived from them a set of field equations governing the curvature of spacetime, which in turn governed the motion of matter and energy, which in turn determined the curvature, a closed, self-consistent system of extraordinary mathematical depth and physical scope. Einstein wasted no time in applying it. In 1917, seeking to describe the universe as a whole using his new field equations, he found that the equations did not naturally produce a static universe. They implied either expansion or contraction. Since the astronomical consensus of the time held that the universe was static, Einstein introduced an additional term into his equations, a constant that he called the cosmological term, whose effect was to produce a repulsive force at large scales that would exactly balance gravitational attraction and hold the universe in a stable, unchanging configuration. He would later describe this modification as his biggest blunder. When Edwin Hubble's observations in 1929 demonstrated that the universe was in fact expanding, the cosmological term introduced to prevent a conclusion the equations naturally implied had been unnecessary. But the story has an ironic coda. The cosmological constant, dismissed by Einstein as a mistake, was reintroduced by cosmologists in the 1990s to account for the observed accelerating expansion of the universe. It is now a fundamental parameter of the standard model of cosmology. The November 1919 announcement did not just make Einstein famous, it made him into something that fame alone does not usually produce, a global symbol. Within weeks, his face was on the front pages of newspapers in languages he could not read, in countries he had never visited. Strangers wrote to him daily. Invitations arrived from governments, universities, and heads of state. He had not sought any of this, and he found much of it bewildering. But the celebrity did not arrive in a vacuum. It arrived in a Germany that was economically shattered, politically unstable, and culturally volatile in ways that made Einstein's sudden prominence a target as much as a triumph. Germany had lost the First World War. The Kaiser had abdicated. The Weimar Republic was less than a year old, fragile and contested from its first days. In this environment, a Jewish physicist from Berlin, being celebrated by British scientists, the former enemy, for overturning the physics of Isaac Newton was, for a significant portion of the German nationalist press, not a source of pride. It was a provocation. The attacks came quickly and with considerable venom. Nationalist critics argued that relativity theory was not genuine science, but a form of Jewish intellectual deception, abstract, unverifiable, designed to undermine the solid empirical traditions of German physics. The phrase Jewish physics began to circulate in these circles, contrasted unfavourably with what the attackers called Aryan physics, concrete, experimental, grounded in observable reality rather than mathematical abstraction. This was not a fringe position. It had vocal proponents among credentialed physicists, most prominently Philipp Lenard and Johannes Stark, both Nobel Prize winners, both of whom would later become enthusiastic supporters of the Nazi regime, and leading figures in the campaign to purge Jewish scientists from German institutions. Their opposition to Einstein was framed in scientific language, but operated on openly anti-Semitic premises. Einstein responded publicly, which was itself a departure from the conduct most scientists of his generation would have considered appropriate. He wrote in professional journals and in popular newspapers. He gave interviews. He did not retreat into the laboratory and wait for the controversy to pass. He identified the attacks as anti-Semitic and said so plainly at a time when many of his colleagues preferred to treat them as scientific disputes that happened to involve a Jewish scientist. This was the beginning of a pattern. Einstein was becoming not just a physicist who had opinions about politics, but a public intellectual who understood that his visibility gave him a platform and who was willing to use it. The transition was not entirely comfortable for him, and it was not always comfortable for those around him. But it was genuine. In 1920, he became a target of organised public harassment. A meeting was held at the Berlin Philharmonic specifically to attack relativity theory. Einstein attended, sitting in a box, watching the proceedings against him with what observers described as an expression of calm amusement. He was not amused in any simple sense, but he had already developed the habit of treating institutional hostility as evidence that something important was at stake. His growing identification with the Jewish community was in some respects new. The Einstein family had been largely non-observant, assimilated in the German Jewish bourgeois tradition. Einstein himself had no strong religious attachments and would not develop conventional ones, but the organised anti-Semitism he encountered after 1919 pushed him toward a different kind of Jewish identity, not religious, but cultural and political. In 1921 he travelled to the United States for the first time, accompanying Chaim Weizmann on a fundraising tour for the Hebrew University in Jerusalem. He met President Warren Harding at the White House. He lectured at Princeton. He gave interviews in which he spoke openly about the need for a Jewish cultural and intellectual home in Palestine, framing it in terms that were more about the dignity of a persecuted people than about theological conviction. This was a significant public commitment. it also complicated his reception in some quarters. He was now not just a controversial physicist, but a visibly Zionist one, which added another layer of political identity to an already politically charged public presence. Through all of this, he continued working. The Nobel Prize came in 1922, awarded for 1921, for the discovery of the law of the photoelectric effect, the result he had derived in the first of the 4 papers of 1905. The Nobel Committee's citation conspicuously did not mention the theory of relativity, still considered controversial enough that the committee preferred to honour a result with more direct experimental confirmation. Einstein was in Japan when the award was announced and learned of it through a telegram. The prize money, as agreed in the divorce settlement negotiated years earlier, went to Mileva Maric. October 1927. Brussels, the Fifth Solvay Conference. The guest list read like a census of everyone who mattered in physics at that moment. Lorentz, Planck, Bohr, Born, Heisenberg, Schrödinger, Dirac, de Broglie, Pauli, Curie. 29 physicists in total, representing between them virtually the entire architecture of modern physical theory. A photograph taken during the conference shows them arranged in 3 rows. Einstein sits in the centre of the front row. He looks composed. He looks, if anything, slightly amused. He was not there to celebrate. He was there to fight. The official subject of the Fifth Solvay Conference was the new quantum mechanics, the framework that Heisenberg, Born, Jordan, Schrödinger and Dirac had assembled between 1925 and 1926. By October 1927, it was already producing results of remarkable precision. Its mathematical predictions matched experimental observations across a wide range of atomic phenomena. By any practical measure, it worked. The question the conference was really there to address was a harder one. What did it mean? Niels Bohr had an answer. It was called complementarity, and it had been developed during the preceding months in intense discussions with Heisenberg and others at Bohr's Institute in Copenhagen. Complementarity held that quantum phenomena were genuinely and irreducibly dual in nature. An electron, for instance, was neither a particle nor a wave in any classical sense. It was something for which classical physics had no adequate description. Depending on the experimental arrangement chosen, depending on what the observer decided to measure, it would display particle-like or wave-like behaviour, but never both simultaneously. This was not a limitation of current knowledge. It was a fundamental feature of reality at the quantum level. More significantly, Bohr argued that the quantum mechanical description of a system was complete. There was nothing underneath the probability wave, no hidden set of definite values for position and momentum that the wave was averaging over. When quantum mechanics said an electron had a probability of being found in a certain region, that probability was not a reflection of ignorance about a definite location. It was the full description of the electron's physical situation. The electron did not have a definite location until it was measured. The act of measurement did not reveal a pre-existing property. It brought the property into being. Einstein listened to all of this carefully. Then he started producing thought experiments. Every morning of the conference, Einstein would arrive at breakfast with a new argument, a carefully constructed hypothetical scenario designed to show that quantum mechanics, if taken seriously as a complete description of reality, led to a contradiction or an absurdity. The thought experiments were not idle provocations. They were precisely constructed physical scenarios, internally consistent, that seemed to demonstrate that an electron could be shown to have a definite position and momentum simultaneously, in violation of Heisenberg's uncertainty principle, which Bohr's interpretation treated as a fundamental law of nature rather than a practical limitation. Bohr would work through the day on his response. By dinner, he had an answer. The answer was always, in essence, that Einstein had overlooked some physical constraint, some feature of the experimental apparatus, some unavoidable disturbance introduced by the measurement process itself, that, when properly accounted for, restored the uncertainty principle and left the quantum mechanical description intact. The other physicists at the conference watched this exchange with a mixture of admiration and unease. Heisenberg, who had constructed the uncertainty principle, later recalled feeling anxious each time Einstein presented a new argument, not because he believed Einstein was right, but because the arguments were good enough that he could not immediately see the flaw. Pauli, characteristically blunt, reportedly muttered to Heisenberg that Einstein was behaving like an anti-relativity crank, which was both unfair and understandable, given the frustration the younger physicists felt. Paul Ehrenfest, a close friend of both Einstein and Bohr, watched the exchange with what the historical record describes as genuine distress. He wrote afterward that it had been electrifying, but also painful, like watching two people he loved argue in a language that each was using slightly differently, neither quite hearing what the other was actually saying. That observation was more precise than it might appear. Einstein and Bohr were not simply disagreeing about quantum mechanics. They were disagreeing about what a physical theory is supposed to do, what counts as a complete description of nature, what the relationship between mathematics and physical reality actually is, and whether probability in the quantum mechanical sense represents genuine indeterminism in nature or merely incomplete knowledge of an underlying deterministic reality. These were not questions that could be settled by calculation. They were philosophical commitments, and both men held theirs with the kind of conviction that does not yield easily to counter-argument. Einstein's position, stated plainly, was this: a complete physical theory must describe the actual state of a physical system, what the system actually is, independent of whether anyone is observing it or measuring it. Quantum mechanics, in Bohr's interpretation, could only describe what would be found if a measurement were made. It said nothing about what the system was doing between measurements. For Einstein, this was not a deep philosophical insight. It was a confession of incompleteness. Bohr's position, equally plainly, was that Einstein's demand for a description of an unmeasured system was based on a classical intuition that simply did not apply at the quantum level. The question, what is the electron doing when no one is looking, was not a question that nature was obliged to answer. It might be a question that had no physical meaning. Asking it was like asking what is north of the North Pole, not difficult but meaningless. By the end of the conference, the physics community had largely aligned with Bohr. This was not because Einstein's arguments had been definitively refuted in every case. It was partly because the new quantum mechanics was producing results that nothing else could match, and most physicists were more interested in using the framework than in interrogating its philosophical foundations. It was also because Bohr's responses, while not always fully worked out in the moment, were generally considered adequate by the standards of the field. Einstein had not found a crack that stayed open, but Einstein did not concede. He accepted that his morning arguments had been answered. He did not accept that the underlying objection had been addressed. The distinction matters. Einstein was not claiming that quantum mechanics gave wrong predictions. He was claiming that correct predictions were not sufficient to establish that a theory was complete. A theory that predicted only probabilities, that described only what measurements would find rather than what systems actually were, was for Einstein a stepping stone. A remarkably successful approximation to something deeper that had not yet been found. He was prepared to acknowledge the success of the framework, while continuing to deny that it represented the final word on the nature of physical reality. This position was not irrational. It was, in fact, a coherent scientific stance. The view that a phenomenologically successful theory might still be incomplete at the level of fundamental description. Newtonian gravity had been phenomenologically successful for over 2 centuries before general relativity revealed the deeper structure underneath it. Einstein was not claiming that quantum mechanics would be overturned. He was claiming that it would be subsumed, that a future theory would explain why its probabilistic predictions were correct, in the same way that statistical mechanics explained why thermodynamics worked, by revealing the underlying deterministic reality that the probabilistic description was averaging over. Before the story moves forward in time, it needs to pause here, because the debate at Solvay is frequently reduced to a slogan. Einstein said, "God does not play dice." Bohr told him to stop instructing God, and that reduction costs us almost everything that makes the argument worth understanding. Both positions deserve a fair hearing. Neither man was being stubborn without reason, and the question of who was right is not as settled as most popular accounts suggest. Start with Bohr. Niels Bohr was a Danish physicist who had built his reputation on the 1913 model of the hydrogen atom, the model that introduced discrete electron orbits and explained the hydrogen spectrum in terms of quantum jumps between those orbits. By 1927, he had spent over a decade thinking harder than almost anyone else about what quantum phenomena actually required of physical theory. His concept of complementarity was not a hasty philosophical patch. It was a carefully developed response to a genuine puzzle. The puzzle was this. In classical physics, a physical object has definite properties, a position, a momentum, a trajectory, that exist independently of whether anyone measures them. Measurement, in classical physics, is in principle a passive act. It reveals what is already there. The difficulty in quantum mechanics was that this picture broke down completely. If you designed an experiment to measure an electron's position precisely, you disturbed its momentum irreversibly. If you designed it to measure momentum precisely, you lost information about position. This was not a technological limitation. It was built into the mathematical structure of the theory through the commutation relations that Born had identified in 1925. Bohr's response was to take this seriously at the deepest level. He argued that the classical concepts of position and momentum were not features of the electron itself, but features of the experimental arrangements used to investigate it. An electron does not have a position independent of a position measurement. It does not have a momentum independent of a momentum measurement. The two properties are complementary. Each is well defined only in experimental contexts that exclude the other. This is not a limitation of human knowledge. It is a statement about the nature of physical reality at the quantum level. The wave function, the mathematical object that quantum mechanics uses to describe a system, encodes all the probabilities for all possible measurement outcomes. When a measurement is made, the wave function changes discontinuously, updating to reflect the result. For Bohr, this was not a mysterious process requiring further explanation. It was simply what measurement meant at the quantum level. This framework was internally consistent. It made no false predictions. It explained the experimental results with extraordinary precision, and it had a certain philosophical austerity that some physicists found compelling, a refusal to speculate about what systems were doing when not being observed, an insistence on staying close to what could actually be measured and said. Now consider what Einstein found inadequate about it. Einstein's objection was not that quantum mechanics gave wrong answers. He accepted the predictions. His objection was that a theory which could only speak about measurement outcomes, which was silent about the state of a system between measurements, was not a complete description of physical reality. It described the interface between the quantum world and the measuring apparatus. It did not describe the quantum world itself. He held what philosophers of science call a realist position. He believed that physical systems have definite properties whether or not those properties are being measured. The moon exists when no one is looking at it. An electron has a position even when no position measurement is being made. A theory that could not assign definite properties to unmeasured systems was, for Einstein, not a final theory, but a provisional one. Accurate as far as it went, but pointing towards something deeper that it could not itself describe. This was not a naive position. It was the assumption underlying every physical theory from Newton through Maxwell, through general relativity. In all of those theories, the mathematical objects of the theory correspond to features of physical reality that exist independently of observation. Einstein was not defending classical physics. He was defending a methodological commitment, a view about what physical theories are supposed to be descriptions of. Bohr's counter was that this commitment, however successful it had been in classical physics, could not be extended to the quantum domain without contradiction. The experimental evidence demanded a different picture. Asking what an electron was doing between measurements was not a deep question awaiting a deep answer. It was a question the evidence had rendered meaningless. Nature, at the quantum level, simply did not provide the kind of objective, observer-independent description that Einstein was demanding. Neither position was obviously wrong, and this is the point that most popular accounts of the debate obscure by declaring Bohr the winner. Bohr's framework survived every experimental test that could be designed with the technology available at the time. But survival of experimental tests is not the same as being the uniquely correct interpretation of a mathematical framework. Quantum mechanics as a mathematical structure is compatible with multiple interpretations. Bohr's Copenhagen interpretation, the many worlds interpretation developed by Hugh Everett in the 1950s, the pilot wave theory developed by David Bohm in 1952, and several others. These interpretations make the same experimental predictions, but describe physically different realities. The experimental evidence alone cannot choose between them. Bohm's pilot wave theory, developed more than 2 decades after the Solvay confrontation, is particularly relevant here. It is a fully deterministic realist theory, exactly the kind of thing Einstein had argued must in principle be possible, that reproduces all the predictions of standard quantum mechanics. Einstein was aware of it before he died and expressed qualified interest, though he did not regard it as the final answer he had been looking for. Its existence nonetheless demonstrates that Einstein's demand for a realist, deterministic completion of quantum mechanics was not logically impossible, as Bohr and his followers sometimes implied. It was merely unfashionable. The deeper issue was causality. Einstein's commitment to a deterministic description of nature rested on a belief that every physical event has a sufficient prior cause, that nature does not, at the fundamental level, simply roll dice. Quantum mechanics, in Bohr's interpretation, violated this. Spontaneous emission, radioactive decay, the outcome of a measurement on a quantum system, these were events for which the theory assigned probabilities, but offered no prior cause. They happened, statistically, at the rates the theory predicted. Why any particular one of them happened when it did was a question the theory declared unanswerable. Einstein had flagged his discomfort with this as early as 1916, in the paper on spontaneous and stimulated emission, where he called the acausal character of individual quantum transitions a weakness of the theory. By 1927, that discomfort had solidified into a principled refusal to accept acausality as a permanent feature of the description of nature. While Einstein was debating the foundations of physics in Brussels, Mileva Maric was in Zurich managing a life that had grown steadily harder since the divorce was finalised in 1919. The properties she had purchased with the Nobel Prize money provided a modest income. It was enough to maintain a household, but not enough to absorb what was coming. Her older son Hans Albert was completing his engineering studies and would eventually build a stable career of his own. Her younger son Eduard was showing early signs of the illness that would consume the second half of her life. Eduard Einstein was, by all accounts from those who knew him as a young man, genuinely gifted. He was musically talented. He played the piano with real ability and spoke with admiration about Schubert and Chopin. He was intellectually curious in ways that seemed to echo both of his parents. He had a sensitivity that people who knew him remembered long afterward. He also began in his early 20s to show signs of psychosis. The precise diagnosis he eventually received was schizophrenia. He experienced breaks from reality, periods of extreme instability, episodes that required hospitalization. By his mid-20s, the illness had become the defining fact of his adult existence. Maric devoted herself to his care with a totality that left little room for anything else. She managed his hospitalizations, his medications, his living arrangements, his financial needs. She did this largely without institutional support and almost entirely without Einstein's physical presence. Einstein contributed money when asked. What he did not contribute was proximity. He had left Europe in December 1932 for what was presented as a temporary visit to the California Institute of Technology in Pasadena. He never returned. After January 1933, the Atlantic Ocean separated him from his son permanently. He saw Eduard for the last time before boarding a ship in 1933. Eduard was 23 years old. This is a fact that Einstein's admirers have generally handled carefully, and his critics have sometimes handled reductively. The full picture is neither straightforwardly excusable nor straightforwardly damning. Einstein did not abandon Eduard without awareness of what he was doing. His letters from the American years contain references to Eduard that are not cold. He expressed concern. He sent money. He was aware of the weight Maric carried, but awareness and action are different things. And the action he took, staying in Princeton, maintaining the ocean between himself and his son, had consequences for Eduard and for Maric that Einstein did not have to live with directly. There is a letter Einstein wrote to a friend in the 1930s in which he described his relationship with Eduard as one of the great sorrows of his life. The letter is genuine in its pain. It is also written from a safe distance. Maric had no such distance. She was in the room. She managed Eduard's care until her own health began to fail in the 1940s. She suffered a series of strokes. By 1947, her physical condition had deteriorated to the point where basic daily tasks required assistance. She died in August 1948 in Zurich, in the apartment she had shared with Eduard for years. She was 72 years old. After her death, Eduard was transferred to a psychiatric clinic called the Burghölzli in Zurich, where he would live for the rest of his life. He remained there until his death in 1965, outliving his father by 10 years. Einstein did not return to Europe to see him. The reasons were partly political. Returning to Europe after 1933 was complicated by the circumstances of his departure and by the new political geography of the post-war world. But they were also in some measure a reflection of a pattern that had been established long before the politics made it easy to justify. Einstein's private correspondence from the Princeton years contains occasional references to the guilt he felt about Eduard. These references are real, not performed, but they sit alongside evidence of a man who had organised his inner life in a way that kept certain kinds of pain at a manageable distance, that allowed him to grieve without being consumed by grief, to feel responsible without allowing responsibility to redirect the work. That capacity for emotional compartmentalization was not unique to his relationship with Eduard. It was a feature of how he had navigated his relationship with Mileva during the marriage, his relationship with his first daughter Liesel, and his relationship with the broader consequences of decisions he made throughout his life. It enabled him to work with extraordinary focus under conditions that would have paralysed many people. It also meant that the costs of his decisions were absorbed in disproportionate measure by the people closest to him rather than by him. Elsa Löwenthal, Einstein's second wife, managed the domestic architecture of his Princeton years with considerable competence and without, as far as the record shows, much acknowledgement. She handled correspondence, managed household logistics, navigated the social demands of his celebrity, and created the conditions in which he could work. She died in December 1936 after a prolonged illness, 2 years after the couple had settled permanently in Princeton. Einstein grieved, then returned to work. He had, by all accounts, genuine affection for Elsa. He had also, during their marriage, maintained other relationships, whose details emerged primarily from letters that became available to scholars over subsequent decades. He did not treat fidelity as a priority. He did not appear to regard this as requiring significant justification. His letters on the subject, when he addressed it at all, suggest a man who considered the emotional demands of conventional marriage to be in tension with the kind of concentrated intellectual life he required, and who resolved that tension consistently in favour of the intellectual life. What this produced in aggregate was a pattern. The women in Einstein's life, Maric, Elsa and others, organised themselves around his needs. When those needs changed, or when maintaining the arrangement became too costly, the reorganisation happened on terms that Einstein set. The costs of the reorganisation were paid primarily by others. Einstein was in Pasadena, California, when Adolf Hitler was appointed Chancellor of Germany on January 30th, 1933. He had been there since December 1932, ostensibly for a 3-month visiting position at the California Institute of Technology. He had made similar visits before to Caltech, to other American institutions, and had always returned to Berlin. This time, standing on American soil and reading the news from Europe, he understood almost immediately that the visit was permanent. He did not announce this dramatically. He did not make a public statement in those first days, declaring that he would never return. He simply began, quietly and methodically, making decisions consistent with a man who knows he is not going home. On March 28, 1933, arriving in the Belgian port of Antwerp after the Atlantic crossing, Einstein walked into the German consulate and surrendered his passport. He formally renounced his German citizenship for the second time in his life. The first had been in 1896 to avoid military service as a teenager. He simultaneously resigned from the Prussian Academy of Sciences, the institution that had offered him the most prestigious scientific position in Germany nearly 2 decades earlier. The Academy's response was not gracious. Several of its members released a statement suggesting that Einstein's departure was no great loss, and implying that his political statements had been damaging to Germany. Max Planck, then the Academy's secretary, navigated the episode with the careful neutrality of a man trying to preserve an institution he loved under conditions that made honest speech dangerous. He wrote to Einstein personally. The letter was pained and somewhat evasive. The friendship between the two men, which had been genuine and intellectually productive for decades, did not survive the political rupture intact. The Berlin apartment Einstein had shared with Elsa on Haberlandstrasse was raided by the authorities. Documents were seized. Most of his papers had been quietly moved to the French embassy beforehand, a precaution that suggests Einstein had anticipated the possibility of exactly this kind of action. The books and personal belongings that remained were confiscated. German newspapers reported that his summer cottage in Kaputh, outside Berlin, had been found to contain a cache of weapons. This was false. The cottage contained a bread knife. The regime moved quickly to consolidate its control over German scientific institutions. Jewish scientists were removed from their positions under the law for the restoration of the professional civil service, enacted in April 1933. The law applied to universities, research institutes, and government agencies across Germany. In a single legislative stroke, it effectively ended the careers of dozens of physicists, mathematicians, and chemists who had collectively made German science the most productive in the world during the preceding 3 decades. The human consequences were immediate and severe. Some scientists emigrated. Some did not move quickly enough. Some stayed out of attachment to Germany. Disbelief that the situation would worsen, or inability to secure positions elsewhere. Of the physicists who remained, a significant number eventually died in concentration camps. Einstein threw himself into the work of helping those who were trying to leave. He used his international connections, which were by this point among the most extensive of any scientist alive, to write letters of recommendation, to contact universities, to advocate for positions for refugee scholars in Britain, France, Switzerland, and the United States. The Emergency Committee in Aid of Displaced Foreign Scholars, established in New York in 1933, became one of the primary channels through which Einstein and others worked to find academic appointments for those fleeing Germany. He was tireless in this effort in a way that contrasted sharply with the emotional distance that characterized other aspects of his personal life. He gave a lecture at the Royal Albert Hall in London in October 1933, speaking before an audience of roughly 9,000 people at a benefit for refugee German scholars. He spoke in English, which he had been using with increasing facility since his first American visits. The speech was measured and serious. He described the situation in Germany without hyperbole and without sentimentality, and he made the case for the importance of intellectual freedom as a condition for scientific progress. A week later, he boarded a ship for the United States. He arrived in New York on October 17th and reached Princeton that evening. He would not leave the country for an extended period again. The Institute for Advanced Study in Princeton had been established in 1930 with a mandate to provide permanent positions to scholars of the highest distinction, free from teaching obligations and institutional pressures. Einstein had been offered one of the 6 founding professorships in 1932, before the political situation in Germany had reached its crisis point. He had accepted, pending resolution of his Berlin commitments. After January 1933, the resolution was straightforward. Princeton suited him in some respects and baffled him in others. He walked to the institute each day along Mercer Street, often stopping to talk with students or neighbours. He played the violin. He went sailing when weather permitted. Though his skills as a sailor were, by multiple accounts, more enthusiastic than accomplished, he cultivated a studied informality that charmed some and puzzled others. What Princeton could not provide was the scientific community he had left behind. Berlin in the 1920s had been, despite everything, one of the most intellectually stimulating environments in the world. The institute was quieter, more isolated, and in the early years, somewhat self-consciously prestigious, in a way that Einstein found faintly comic. He worked there for the rest of his life, and he valued the freedom it gave him. But the creative friction of the Berlin years, the proximity to Planck, to colleagues who would argue back, to to a city that hummed with scientific energy, was gone. The Germany he had left behind was dismantling itself scientifically with a thoroughness that was almost systematic. The phrase Jewish physics that had circulated in nationalist circles since the early 1920s was now institutional policy. Philipp Lenard and Johannes Stark, who had been attacking Einstein's work since the 1920s on openly anti-Semitic grounds, now had the political wind at their backs. Lenard published a 4-volume work called German Physics that systematically excluded Jewish scientists from the history of the field and promoted an alternative account centred on experimental, empirical work, as opposed to the mathematical abstraction he associated with Jewish influence. The irony was that the physics Germany was attempting to practice without its Jewish scientists was not functional at the same level. The emigration of talent that the Nazi racial laws produced, not just Jewish scientists, but anyone whose political or personal commitments made Germany uninhabitable, represented one of the greatest self-inflicted intellectual wounds in the history of any nation. The physicists who left Germany and German-speaking Europe between 1933 and 1940 contributed enormously to the scientific capacity of their host countries, particularly the United States and Britain. The Manhattan Project, when it eventually assembled, drew heavily on this pool of displaced European talent. Before the summer of 1939 arrives, there is a paper that needs to be examined, because what Einstein did in the summer of 1939 was shaped in part by who he understood himself to be. A scientist, not a weapons designer, not a political actor, not a symbol. And understanding who he understood himself to be in 1939 requires understanding what he had spent 1935 doing. In May 1935, the Physical Review published a short paper by Einstein, Boris Podolsky, and Nathan Rosen, 2 assistants at the Institute for Advanced Study. The paper was titled, "Can Quantum Mechanical Description of Physical Reality be Considered Complete?" It was 4 pages long. It was, in retrospect, one of the most consequential papers published in the 20th century. At the time, most physicists read it as the complaint of a brilliant man who had not kept pace with the developments of his field. The argument was precise and carefully constructed. It began with 2 criteria that Einstein, Podolsky and Rosen considered minimal requirements for any adequate physical theory. The first was a reality criterion. If the value of a physical quantity can be predicted with certainty, without disturbing the system in any way, then there exists an element of physical reality corresponding to that quantity. The second was a completeness criterion. A complete theory must contain a counterpart for every element of physical reality. They then constructed a scenario, a thought experiment involving 2 particles that had interacted and then separated, moving apart to an arbitrarily large distance. According to quantum mechanics, the wave function describing the pair remained connected even after separation. Measuring the position of one particle would instantaneously determine the position of the other with certainty without touching the second particle. By the reality criterion, the position of the second particle was therefore an element of physical reality, but the same argument applied to momentum. Measuring the momentum of the first particle would instantaneously determine the momentum of the second, with certainty without touching it. So the momentum of the second particle was also an element of physical reality, but quantum mechanics, through the uncertainty principle, insisted that a particle could not simultaneously have a definite position and a definite momentum. If both were elements of physical reality, as the argument appeared to show, then quantum mechanics was failing to represent them both. It was, by the completeness criterion, incomplete. The argument was not claiming that quantum mechanics gave wrong predictions. It was claiming that the theory was silent about aspects of physical reality that actually existed. Somewhere underneath the probability wave, definite properties were present that quantum mechanics could not see. Erwin Schrödinger read the paper immediately and wrote to Einstein with enthusiasm, coining in his response the term that would eventually define the phenomenon at the paper's centre. He called it Verschränkung, entanglement, the condition in which two particles that have interacted remain correlated in ways that cannot be explained by any information they carried away from the interaction. Schrödinger followed his letter with a paper of his own, published later that year, in which he described the entanglement concept in detail and introduced a thought experiment that has become the most famous in the history of physics. A cat is placed in a sealed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers a mechanism that breaks the vial and kills the cat. Quantum mechanics, applied to the whole system, produces a wave function in which the cat is neither alive nor dead, but in a superposition of both states, until the box is opened and an observation is made. Schrödinger intended this not as a cute puzzle, but as a reductio ad absurdum, a demonstration that applying quantum mechanics to macroscopic objects produced descriptions of reality that were literally nonsensical. Bohr's response to the EPR paper came quickly. It was published in the same journal, Physical Review, later in 1935. His argument was characteristically dense and has been interpreted in different ways by different philosophers of physics in the decades since. The core of it was that Einstein, Podolsky and Rosen had assumed, without justification, that the properties of the two separated particles existed independently of whatever measurement arrangements were chosen to investigate them. In Bohr's framework, the properties of a quantum system were not separable from the experimental context in which they were defined. The two particles, having interacted, remained a single quantum system in a meaningful sense. Speaking of the position or momentum of one particle, independently of the measurement context applied to the other, was for Bohr simply not permissible. This response did not satisfy Einstein. He wrote to Schrödinger that Bohr's reply had not engaged with the actual argument. Bohr had redescribed the framework rather than answered the challenge within it. The question of whether the framework itself was adequate, whether the correlations between the two particles could be explained without invoking some kind of instantaneous connection across arbitrary distances, remained, in Einstein's view, open. Einstein called the apparent instantaneous connection implied by entanglement spukhafte Fernwirkung, spooky action at a distance. The phrase was pointed. It echoed the language Newton had used to dismiss his own theory of gravity as philosophically unsatisfactory. Action at a distance without a medium of transmission had struck Newton and his contemporaries as a cult. Einstein was suggesting that quantum mechanics, in Bohr's interpretation, had reintroduced exactly the kind of non-local instantaneous influence across space that physics had spent 2 centuries trying to eliminate. His own preference was for what he called local realism, the view that physical systems have definite properties at definite locations, and that the properties of one system cannot be instantaneously affected by what is done to another system at a distant location. This was not an arbitrary preference. It was grounded in special relativity, which established that no signal, influence, or causal connection could propagate faster than the speed of light. If measuring one particle instantaneously affected the state of another particle at an arbitrary distance, something seemed to be travelling faster than light. Einstein found this unacceptable. The physics community's response to the EPR paper was, for the most part, dismissal. Not hostile dismissal, The paper was taken seriously enough to receive a formal reply from Bohr, but the kind of dismissal that comes from a field that has moved on and does not feel the need to revisit settled questions. Quantum mechanics worked. The EPR paper raised philosophical objections. Philosophical objections in a field producing results of extraordinary practical and theoretical power were not high priority. The paper disappeared, largely into the background noise of the literature. It was cited occasionally. It was not regarded as an active research problem. For nearly 3 decades it sat there, a careful argument that the most precise physical theory ever constructed was missing something. Written by the man who had helped build the framework that theory rested on, ignored by the practitioners who were too busy using the theory to ask what it was actually saying about reality. Then, in 1964, a paper appeared in the journal Physics by a Northern Irish physicist named John Stuart Bell, working at the CERN laboratory in Geneva. Bell had taken the EPR argument seriously, more seriously than almost anyone else in the intervening decades, and had done something Einstein had not done. He had turned the philosophical question into a mathematical one. Bell showed that if local realism was correct, if the correlations between the two entangled particles were the result of definite properties they carried away from the interaction, rather than some instantaneous non-local connection, then those correlations had to satisfy certain mathematical inequalities. The inequalities expressed in precise quantitative terms the limits on how strongly correlated two particles could be if their properties were determined locally and in advance. Quantum mechanics predicted correlations that violated those inequalities. The two predictions, local realism and quantum mechanics, disagreed. And the disagreement was, in principle, measurable. Bell's inequalities transformed the EPR argument from a philosophical dispute into an experimental question. If experiments found correlations that violated Bell's inequalities, local realism was wrong, and Einstein's intuition about spooky action at a distance, whatever one thought of its interpretation, was pointing at a genuine feature of nature. If experiments found correlations that satisfied the inequalities, quantum mechanics would need revision. July 1939. Peconic, Long Island. Einstein was on vacation. He was renting a small house near the water, sailing when he could, working on the unified field theory problem that occupied most of his Princeton hours. The summer had the quality of temporary relief. From the Institute's social obligations, from the mail that arrived daily in quantities that no single person could reasonably process, from the accumulated weight of being Albert Einstein in a world that had increasingly difficult demands to make of their identity. Leo Szilard arrived without much warning. Szilard was a Hungarian-born physicist who had emigrated from Germany in 1933, one of the same wave of displaced European scientists who had dispersed across Britain and America after the Nazi racial laws came into effect. He was not a man given to understatement or excessive caution. He had been thinking for years about the military implications of nuclear physics, and by the summer of 1939 he had specific reasons for urgency. In December 1938, the chemists Otto Hahn and Fritz Strassmann, working at the Kaiser Wilhelm Institute in Berlin, had conducted experiments on uranium that produced a result neither of them initially understood. Their colleague Lise Meitner, who had fled Germany earlier that year and was working in Sweden, interpreted the result with her nephew Otto Frisch in December 1938. Uranium nuclei, when struck by neutrons, were splitting apart. The process released energy. It also released additional neutrons. Those neutrons could, in turn, strike other uranium nuclei, releasing more energy and more neutrons. The word for this was fission. The implication, which Szilard grasped almost immediately, with a clarity that several other physicists were slower to reach, was that a sufficiently large mass of uranium could sustain a chain reaction, a self-amplifying cascade of fission events, releasing energy at a rate that was not gradual but explosive. The energy equivalent of a small amount of mass, as Einstein's 1905 equation described, was enormous by any conventional measure. Concentrated and released rapidly, it could produce a weapon of entirely new destructive capacity. Szilard knew that German physicists understood this. He knew that Germany had access to uranium ore from mines in the Belgian Congo, which Belgium controlled. He knew that the Belgian government was not necessarily aware of the strategic significance of those mines in this new context. And he knew that the person most likely to be listened to by the Belgian government and by the American government on a matter touching on physics and international affairs was the man sitting in the rented house in Peconic. He brought with him another Hungarian physicist, Edward Teller, who drove. Einstein listened. What Einstein knew about nuclear fission at that moment is a matter of some historical interest. He later said that the possibility of a chain reaction had not occurred to him, and that Szilard's explanation came as a surprise. This is plausible. Einstein's work after 1915 had been almost entirely in the areas of general relativity, unified field theory, and the quantum debate. Nuclear physics, as a specialized field, had developed largely independently of the theoretical concerns that occupied him. He had not been following the fission experiments closely. He understood, once Szilard explained, what the implications were. The conversation that afternoon in Peconic produced a decision. Einstein would lend his name and his signature to a letter addressed to President Franklin Roosevelt, warning that recent developments in nuclear physics had opened the possibility of an extremely powerful new type of bomb, and that Germany might be actively pursuing this possibility. The letter recommended that the United States government take the matter seriously, establish contact with the physics community, and consider how to secure supplies of uranium before they fell under Axis control. The letter went through several drafts. Szilard wrote the primary text. Einstein reviewed it and suggested modifications. A shorter version and a longer version were prepared. Ultimately, the longer one was sent. The process of getting the letter to Roosevelt took longer than expected. The original intermediary Szilard had identified to deliver it, an economist named Alexander Sachs, who had access to the president, did not arrange the meeting until October 11th, 1939. By that point, Germany had invaded Poland 6 weeks earlier, and the war in Europe had begun. Roosevelt read the letter and reportedly said, "This requires action." He established an advisory committee on uranium, which met for the first time that same month. The committee was small, underfunded, and moved slowly. The path from that first committee to the Manhattan Project, the full-scale American program to develop an atomic weapon, was not a straight line. It passed through several reorganizations. A British program called the Maud Committee, whose conclusions were more urgent than anything the Americans had produced, and the political pressure of a war that by late 1941 had drawn the United States in directly. Einstein played no role in any of this beyond the letter. He was not invited to participate in the Manhattan Project. The reason was his security clearance, or rather its absence. The army officers overseeing the project and the security apparatus surrounding it reviewed Einstein's file, his associations with pacifist organizations, with socialist groups, with various left-wing causes he had supported publicly over the preceding 2 decades, were deemed to present an unacceptable security risk. The man whose equation described the energy to be released, whose letter had helped initiate the program, was considered too politically unreliable to be trusted with knowledge of what the program was doing. He was aware of this exclusion and did not contest it. He did consulting work for the Navy on conventional explosives during the war a per diem arrangement that began in 1943 and involved no connection to nuclear weapons development. He lived in Princeton, working on unified field theory, while a few hundred miles away, in Los Alamos, New Mexico, a team that included several of the physicists he had known in Europe was building the thing his letter had helped set in motion. He learned that the bomb had been used on Hiroshima on August 6, 1945, from a radio broadcast. His response, as recorded by Helen Dukas, his secretary, was brief. He said, "Oh way," in German, roughly, "Oh no," or more literally, "Oh suffering." 3 days later, a second bomb fell on Nagasaki. Germany had surrendered in May. The justification for the original urgency, that Germany might build the weapon first, had been rendered moot months before the bombs were used. Einstein had not known, and could not have known in 1939, that the German nuclear program would stall, that German physicists would encounter obstacles, both technical and organisational, that prevented them from reaching the critical stages the Americans reached. His letter had been written under the assumption that a race was underway. By 1945, the race had only one contestant. He gave an interview to Newsweek shortly after the bombings. He said, "Had I known that the Germans would not succeed in developing an atomic bomb, I would have done nothing." The statement has been quoted often and analysed carefully. It is honest as far as it goes. It accurately describes his 1939 reasoning. What it does not do is fully account for the question of what he believed his signature would set in motion, or whether a man of his intelligence and political experience could not have anticipated that a weapon, once developed, would be used. That question is not answerable from the evidence available. Einstein's private correspondence from the post-Hiroshima years does not contain a fully worked-out reckoning with his own role. What it contains is genuine distress, expressed repeatedly and without performance, alongside the kind of carefully bounded responsibility that tends to characterise how intelligent people process their involvement in events whose scale exceeds any individual's intentions. He described himself in one of the more quoted formulations from this period as a mailbox. Szilard had written the letter. He had signed it. A mailbox delivers messages. It does not author them, and it does not determine what the recipient does with them. The metaphor is striking precisely because it is so deliberate, so obviously constructed to establish a limit around his responsibility. Whether that limit is the right one is a question that reasonable people have answered differently. What happened after Hiroshima was not passivity. Einstein moved quickly and with genuine commitment into the work of nuclear disarmament advocacy. In May 1946, he was named chairman of the Emergency Committee of Atomic Scientists, a group of physicists who had worked on the bomb and who now organised publicly to warn of the dangers of nuclear proliferation and to advocate for international control of atomic energy. He remained chairman until the organisation disbanded in 1951. The post-war years did not give Einstein rest. They gave him a different kind of pressure, the pressure of being the world's most visible scientist, in a world that had just demonstrated what science could do to a city in roughly 45 seconds. The public wanted reassurance. Governments wanted prestige. The military wanted silence. Einstein offered none of these things in the forms they were requested. What he offered instead was a consistent, sometimes uncomfortable argument that the existence of nuclear weapons had fundamentally altered the political situation of every nation on Earth, and that the institutions designed to manage international conflict, nation-states, military alliances, sovereignty, were no longer adequate to prevent catastrophe. He had been making versions of this argument since the First World War. After Hiroshima, it was no longer a pacifist's preference. It was, in his view, a practical necessity. He returned repeatedly to the idea of a world government, a supranational authority with enough genuine power to prevent nations from going to war with nuclear weapons. This was not a vague aspiration. He wrote about it specifically, argued for it in published essays, and engaged with the objections to it seriously. He knew it was politically remote. He argued for it anyway, on the grounds that the alternative, a world of sovereign nation-states, each capable of developing nuclear weapons, would eventually produce a catastrophe that made Hiroshima look preliminary. The Emergency Committee of Atomic Scientists, which he chaired from 1946, was one vehicle for this advocacy. The committee included several physicists who had worked directly on the Manhattan Project, among them Harold Urey and Hans Bethe, and who now used their technical credibility to warn the public and policymakers about the dangers of the arms race that was already developing between the United States and the Soviet Union. Einstein's role was primarily symbolic in the committee's public work, and he was aware of this. His name on a statement guaranteed coverage. His face on a publication guaranteed attention. He used this deliberately, without apparent embarrassment about the instrumentalism involved. If the icon was useful, the icon could be deployed, but the advocacy had limits that are worth being specific about. Einstein never fully resolved, in public or in private, the question of his own moral position relative to the letter he had signed in 1939. He returned to it in interviews and in correspondence, always with the same framing: the German program, the reasonable fear of being outpaced, the role of a mailbox rather than an author. He did not explore, at least not in any document that has become part of the public record, the question of what he believed would happen to the weapon once it was built. He did not address whether a man of his intelligence and political experience had grounds to anticipate that a weapon developed in wartime would be used in wartime, the bounded responsibility held. This is not a condemnation. It is an observation about how he managed the reckoning, and it matters because Einstein was, in every other context, a man who insisted on intellectual honesty even when it was uncomfortable. The one area where that insistence appears to have softened was the one that implicated him most directly. In 1946, he told a reporter from the New York Times that the release of atomic energy had changed everything except our way of thinking, and that we thus drift toward catastrophe. The line has been quoted so many times that it has lost its sharpness. In its original context, it was a genuine warning, not a rhetorical flourish. He believed it. He also believed that the political will to act on it was not there, and that this gap between what was necessary and what was politically achievable was the central problem of the post-war world. His relationship with Robert Oppenheimer during these years was careful and somewhat constrained. Oppenheimer had directed the Los Alamos laboratory, had built the weapon that Einstein's letter had helped initiate. The two men were colleagues at the Institute for Advanced Study, where Oppenheimer became director in 1947. They were not close in the personal sense, but they respected each other's intelligence and navigated their shared proximity to the bomb's history with a mutual discretion that neither seems to have felt the need to discuss explicitly. When Oppenheimer's security clearance was revoked in 1954, after a hearing by the Atomic Energy Commission that examined his political associations and his past connections to Communist Party members, Einstein advised him not to cooperate with the proceedings. Einstein's position was characteristically direct. The hearing was a political inquisition dressed in bureaucratic language, and engaging with it on its own terms legitimized it. Oppenheimer chose to testify. He lost his clearance. Einstein's assessment of that choice, in private correspondence, was that Oppenheimer had made a mistake, not morally, but tactically, in treating a political attack as if it were a legal one. This episode was part of a broader pattern in Einstein's final decade, the McCarthy period in the United States. The systematic campaign of investigations, blacklists, and loyalty oaths that dominated American political culture from the late 1940s through the mid-1950s produced in Einstein a response that was consistent with everything he had done before and deeply unwelcome to the institutions conducting the investigations. He publicly supported individuals who refused to testify before McCarthy's Senate Internal Security Subcommittee. In a letter to a Brooklyn schoolteacher in May 1953, he advised non-compliance, arguing that the only way to protect intellectual freedom against such proceedings was to refuse to participate in them. The letter was published and produced immediate denunciations from several major newspapers, including the New York Times, which called his advice irresponsible. Einstein did not retract it. He doubled down in subsequent interviews, arguing that the intimidation of intellectuals by government investigations was a greater threat to American democracy than whatever the investigations claimed to be protecting it against. This was not a popular position in 1953. It was also not an inconsistent one for a man who had watched the intimidation of intellectuals by government investigations produce specific historical consequences in the country he had fled 20 years earlier. The FBI file continued to grow. Hoover remained convinced that Einstein represented some form of security risk, though the Bureau's analysts were never able to produce evidence of anything more concrete than political associations that Hoover found objectionable. Einstein was aware of the surveillance and treated it with a mixture of annoyance and philosophical equanimity that suggested a man who had long since concluded that the opinion of security services was not a reliable guide to the importance of what one was doing. In November 1952, Chaim Weizmann, the first president of Israel and a figure Einstein had travelled with to the United States in 1921 on the Hebrew University fundraising tour, died. The Israeli government offered Einstein the presidency. He declined. The reasons he gave were characteristically honest. He said he lacked the natural aptitude and experience for dealing with people and performing official functions. He said he was old and his health was not strong. He said he was deeply moved by the offer and deeply aware of what it represented. All of these things were probably true. What he did not say, but what several people who knew him believed, was that he also understood himself to be constitutionally unsuited to the compromises and constraints of institutional leadership, that the independence he had maintained throughout his life, including the independence to be wrong and to pursue dead ends without accountability to anyone, was not compatible with representing a nation-state. He continued working on the unified field theory. He continued corresponding with physicists on the quantum debate. He continued writing letters on political matters with a frequency that belied his stated belief that his health was failing. There is a version of Einstein's post-1915 career that is told almost exclusively in terms of what he opposed: quantum mechanics, indeterminism, Bohr's Copenhagen interpretation. That version is incomplete, because Einstein was not simply opposing something, he was pursuing something. And the pursuit consumed the last 3 decades of his working life with an intensity that never diminished, even as the results consistently failed to arrive. The project was called Unified Field Theory. The name describes its ambition plainly. Einstein wanted a single mathematical framework that would encompass all the known forces of nature within a geometric description of space-time, the same kind of geometric description that general relativity had provided for gravity. In 1915, gravity had been revealed as the curvature of space-time produced by mass and energy. Einstein wanted to show that electromagnetism, the only other fundamental force recognised by physics in the 1920s, was similarly a geometric feature of an extended spacetime structure, and that from this unified geometry, the quantum behaviour of matter and radiation would emerge as a natural consequence. This was not a modest goal. It was, in the language of contemporary physics, a theory of everything before the phrase existed, before the concept had been formalised, before the strong and weak nuclear forces had been identified as additional fundamental interactions that would also need to be incorporated. Einstein began the pursuit seriously around 1918, almost immediately after completing general relativity. He was not alone initially. Hermann Weyl, a Swiss mathematician of considerable brilliance, proposed in 1918 a geometric theory that extended the Riemannian geometry of general relativity to include electromagnetism through a new mathematical concept involving the parallel transport of vectors in curved space. Einstein engaged with Weyl's theory seriously, arranged its publication in the Proceedings of the Berlin Academy, and then appended a critical objection. The theory, he argued, implied that the measured lengths of physical objects would depend on their history, on the path they had travelled through the field, and this was contradicted by atomic spectroscopy, which showed that atoms of the same element emitted identical spectral lines regardless of where they had been. Weyl's theory did not survive Einstein's objection in its original form, but the approach, using extended geometric structures to unify the known fields, remained the template for what followed. Over the next 3 decades, Einstein pursued a succession of distinct mathematical frameworks, each representing a different approach to the unification problem. The distant parallelism theory of 1928 used a 4-dimensional spacetime equipped with a new geometric structure, a field of orthonormal frames that allowed vectors at different points to be compared directly without the ambiguity that Riemannian geometry introduced through its path-dependent parallel transport. Einstein published the theory in January 1929, and the first printing of the Berlin Academy Proceedings in which it appeared, 1,000 copies, sold out immediately. Newspapers in London and New York reported on it. The theory was displayed in the window of Selfridge's department store in London. A physical theory displayed in a department store window. The public excitement reflected the cultural weight Einstein carried by 1929, rather than the theory's actual prospects. Within 2 years, Einstein himself had abandoned it. It could not produce solutions corresponding to known particles. The field equations it generated were formally elegant, but physically barren. He moved to a series of further approaches, the semi-vector theory of the early 1930s, developed with Walter Mayer, which introduced a new algebraic structure intended to accommodate quantum behaviour within a classical field framework. This too was abandoned. Then came approaches based on an asymmetric metric tensor, a generalization of the symmetric metric tensor of general relativity that introduced additional components intended to accommodate the electromagnetic field. Papers on this approach, co-authored with his last research assistant Brurier Kaufmann, appeared as late as 1954 and 1955, within months of his death. None of these theories worked. None produced results that could be compared with observation in ways that distinguished them from existing theories. None offered any genuine insight into the quantum behaviour of matter that Einstein wanted to derive from first principles. The younger generation of physicists, Heisenberg, Pauli, Dirac, and those who came after them, watched this succession of attempts with a mixture of respect and bewilderment. Pauli, whose opinion on theoretical physics was among the sharpest available, commented more than once that Einstein's unified field theory efforts were misguided, that he was trying to unify the wrong things, using the wrong mathematical tools, under the wrong assumptions about what a fundamental theory needed to do. Pauli was not wrong in his assessment of the specific theories, but his broader implication that the goal itself was misconceived has not aged as well. The pursuit of a unified theory of the fundamental forces of nature is now one of the central projects of theoretical physics. String theory, loop quantum gravity, and various other approaches are all, in their different ways, attempts to do something recognizably similar to what Einstein was attempting. To find a single mathematical framework that encompasses gravity and quantum mechanics within a coherent description of nature. None of these approaches has succeeded either, in the sense of producing a theory that makes testable predictions, distinguishing it from its competitors. The problem Einstein was working on in Princeton between 1933 and 1955 remains unsolved. This does not mean Einstein's specific approaches were on the right track. They almost certainly were not. The mathematical frameworks he explored, Riemannian extensions, distant parallelism, asymmetric metrics, are not the tools that contemporary physicists regard as promising for the unification problem. The strong and weak nuclear forces, which Einstein's program did not incorporate, turn out to be essential components of any adequate unified theory, and their incorporation requires quantum field theory. Precisely the framework Einstein was trying to replace rather than extend. But the instinct that drove the pursuit, the conviction that the fundamental description of nature must be unified, that a theory which requires separate and incompatible frameworks for gravity and quantum phenomena is necessarily incomplete, is the same instinct driving the most ambitious theoretical physics being done today. Einstein was wrong about the solution. He was not obviously wrong about the problem. His working method during the Princeton years was solitary, in a way that struck even sympathetic observers as counterproductive. He worked primarily with a succession of young research assistants: Walther Mayer, Leopold Infeld, Banesh Hoffmann, Valentine Bargmann, Brurier Kaufmann, who provided mathematical support and served as intellectual interlocutors. But he did not engage substantively with the mainstream of theoretical physics as it developed in the 1930s, 40s and 50s. Quantum field theory, which unified quantum mechanics with special relativity and provided the framework for modern particle physics, advanced without him. He was aware of it. He did not regard it as pointing in the direction that interested him. The isolation was partly self-imposed, and partly a consequence of the direction he had chosen. The unified field theory program required a specific kind of sustained, solitary concentration that did not benefit from the kind of collaborative exchange that drove the quantum mechanics program in its productive years. Or at least, that is how Einstein seems to have experienced it. His correspondence with physicists during these years is rich and intellectually engaged on the quantum debate, but relatively sparse on the specific mathematical details of the unified field theory work. As if the core of the project was something he felt needed to be worked through alone. He defended the pursuit explicitly on several occasions. He said he had earned the right to make mistakes. He said, the quest for a unified foundation for physics was a lifelong passion he was not willing to abandon because it was unfashionable, he said, in a 1950 address to the International Congress of Surgeons in Cleveland. An audience that had perhaps not expected to hear about the foundations of physics. That it seemed to him a smile was the best answer to the question of whether the unified theory would ever succeed. The smile was genuine. So was the uncertainty behind it. What is perhaps most striking about the unified field theory years, viewed from a distance, is not the failure. Failure in theoretical physics is common, and the failure of specific approaches tells you something useful about the shape of the problem. What is striking is the consistency of Einstein's philosophical commitments across the entire arc of the work. Every approach he tried shared the same foundational assumptions: that the fundamental theory must be deterministic, that it must be local in the sense of describing fields at definite points in space-time, that it must be geometric in character, and that quantum mechanics must emerge from it as an approximation rather than serving as its foundation. These were not arbitrary preferences. They were the commitments that had produced general relativity, and Einstein saw no reason to abandon them simply because they had not yet produced the next result. The physics community saw reasons to abandon them, or at least to work on different assumptions. The productive direction after 1925 was to accept quantum mechanics as foundational and build upward from it, to develop quantum field theory, to incorporate special relativity, to eventually construct the standard model of particle physics that describes 3 of the 4 fundamental forces with extraordinary precision. This program succeeded on its own terms. It produced the most precisely tested theory in the history of science. It did not incorporate gravity. It still does not. Einstein's prediction that a theory which excluded gravity from its quantum framework was necessarily incomplete has not been falsified. The problem of quantum gravity remains one of the deepest unsolved problems in physics. The unification that Einstein spent 30 years pursuing has not been achieved by anyone. His specific mathematical approaches have not been vindicated. His diagnosis of the problem has not been refuted. The house at 112 Mercer Street was not large by any measure that fame would suggest. It was a white clapboard structure on a quiet residential street in Princeton, New Jersey. Modest, slightly cluttered, with a study on the upper floor where Einstein worked, and a garden that he occasionally sat in when the weather permitted. He had purchased it in 1935, the year Elsa's health began to decline seriously. He lived there for the remaining 20 years of his life without moving. The neighbours grew accustomed to seeing him walk past. Children stopped to talk with him, and he talked back with a patience and genuine interest that multiple accounts describe as real rather than performed. He had no car and no desire for one. He walked. He sailed badly on Carnegie Lake when the season allowed, and he played the violin in the evenings. The domestic texture of the Princeton years was, on the surface, that of a retired professor living quietly in a university town. The surface was misleading. The years between 1945 and 1955 were among the most politically charged of Einstein's public life. The end of the war had not produced the international cooperation he had hoped for. It had produced instead a Cold War between 2 nuclear-armed superpowers, a domestic political climate in the United States defined by suspicion and the systematic persecution of dissent, and a scientific community divided between those who spoke publicly about the dangers of the arms race and those who calculated that silence was the more prudent professional choice. Einstein made no calculation of the second kind. The FBI's interest in him had begun formally in 1933, the year he arrived in the United States. By the late 1940s, the file had grown substantially, and Hoover had developed what can only be described as a fixation on the question of whether Einstein constituted a genuine security risk. The Bureau's difficulty was that the evidence consistently failed to support the conclusion Hoover seemed to have reached in advance. Einstein was not passing information to foreign governments. He was not a member of the Communist Party. He was not engaged in espionage of any kind. What he was doing was publicly associating himself with organizations and causes that the Bureau's analysts flagged as suspicious. The Emergency Committee of Atomic Scientists, various civil liberties organisations, the American Crusade to End Lynching, the National Association for the Advancement of Coloured People. He had signed so many petitions and letters on behalf of so many causes over so many years that the file simply accumulated associations, each one individually innocuous and collectively interpreted by Hoover as evidence of a pattern. The racial justice work deserves specific attention because it is among the less discussed dimensions of Einstein's American years, and because it was not incidental to his broader commitments. Einstein had arrived in the United States from a country where a racial classification system had been used to strip people of their citizenship, their livelihoods, and eventually their lives. His response to the racial segregation he encountered in America was not the polite discomfort of a visitor who prefers not to make scenes. It was a direct and sustained engagement, expressed in public statements, in organisational memberships, and in personal actions. In April 1937, the contralto Marian Anderson came to Princeton to perform a recital. The Nassau Inn, Princeton's main hotel, refused her a room because she was black. Einstein, who had attended the recital, offered her a room in his house on Mercer Street. She accepted. The two remained friends until his death in 1955. He attended her performances when he could and corresponded with her over the years. The gesture in 1937 was not a performance of progressive sentiment. It was a practical response to a specific injustice by a man who had a room available and used it. He joined the NSAACP. He corresponded with W.E.B. Du Bois. He wrote publicly about American racism in terms that drew explicitly on his experience of German anti-Semitism, not to collapse the two histories into one, but to identify a common structure, the use of racial classification to assign different degrees of humanity to different groups of people, with predictable consequences for how those groups were treated by institutions and by law. This was not a popular position for a public figure to take in the 1940s in the United States. It added material to the FBI file. It did not alter his behaviour. The McCarthy period, which gathered force after 1950, presented a different kind of challenge. Joseph McCarthy's Senate Permanent Subcommittee on Investigations and the House Un-American Activities Committee were conducting a systematic campaign of investigations into alleged communist influence in American institutions, universities, the film industry, labour unions, the scientific community. The investigations operated through public hearings in which individuals were summoned to testify, required to answer questions about their political beliefs and associations, and pressured to name others. The consequences of refusing to cooperate were serious. Individuals who declined to answer or who invoked their Fifth Amendment right against self-incrimination faced contempt charges, job loss, and blacklisting. The scientific community was not immune. Several physicists, including Bohm, faced professional destruction as a consequence of their political associations or their refusal to testify. Einstein's response was unambiguous and public. He argued that the investigations were incompatible with the intellectual freedom that made science and democracy possible. He specifically advised individuals who were summoned to refuse to cooperate. His letter to the Brooklyn schoolteacher in May 1953, in which he recommended non-compliance, was the most direct public expression of this position. It attracted immediate condemnation from newspapers that considered it irresponsible advice that encouraged law-breaking. Einstein did not consider it irresponsible. He had watched the progressive restriction of intellectual freedom in Germany during the 1920s and 1930s, and he had watched the eventual consequences of that restriction. He was not willing to stay quiet about a similar process because the country in which it was occurring was the one that had given him refuge. The New York Times editorial board, which had condemned his advice to the schoolteacher, was itself operating under constraints that Einstein did not face. It had institutional interests to protect. He had none. The Institute for Advanced Study would not fire him. His reputation could not be meaningfully damaged by a congressional investigation. He was, in a practical sense, immune to the mechanisms of intimidation that silenced others, and he appears to have been conscious of this immunity, and to have regarded it as carrying an obligation. Oppenheimer's security hearing in 1954 demonstrated what the machinery of investigation could do, even to a figure of considerable institutional standing. Oppenheimer had directed Los Alamos. He had built the weapon. He was the most prominent physicist in America. None of this protected him when the Atomic Energy Commission, responding to pressure from the McCarthy political environment, convened a hearing to review his security clearance. The hearing focused on Oppenheimer's pre-war political associations, his connections to Communist Party members, and his opposition to the development of the hydrogen bomb after the war. Einstein's advice, "do not cooperate," reflected his assessment that the hearing was a political act dressed in procedural language, and that engaging with it on its own terms would legitimize it. Oppenheimer chose to engage. He testified at length. He was forthcoming about his own history and about the histories of others in ways that the hearing's supporters found useful and his supporters found painful. He lost the clearance in June 1954. The official verdict was that he was a security risk. The actual function of the verdict was to remove from public influence a scientist whose opposition to the hydrogen bomb program and whose broader political views the Atomic Energy Commission's leadership found inconvenient. Einstein's comment, in private correspondence, was that Oppenheimer had made a tactical error in treating a political proceeding as if it were a legal one where honest testimony would be evaluated fairly. The comment was not unsympathetic. It was, however, characteristic. The assessment of a man who had navigated institutional hostility for decades by refusing to accept the institution's framing of the situation. His own encounters with American institutional authority had been handled consistently on these terms. He had never sought a security clearance. He had never sought any position that would have required him to accommodate his political views to institutional expectations. The freedom this gave him was the freedom of someone who had deliberately avoided the entanglements that made others vulnerable. By 1954, his health was failing in ways that could no longer be managed by the combination of determination and routine that had sustained him through earlier difficulties. The aortic aneurysm diagnosed in 1948, a dangerous widening of the major abdominal artery, had been managed conservatively, without surgery, because Einstein had declined the operation. He was aware that the aneurysm could rupture. He seems to have accepted this with the same equanimity he brought to other facts he could not change. He continued to walk to the Institute. He continued to work on the field theory. He continued to sign letters and manifestos, and to correspond with physicists, politicians, and ordinary people who wrote to him in quantities that had never diminished. Helen Dukas, his secretary since 1928, managed the correspondence with a loyalty and efficiency that she maintained until her own death in 1982. She inhabited the house on Mercer Street after Einstein's death, protecting his papers and his legacy with a dedication that sometimes shaded into protectiveness, a determination to manage how he was remembered that reflected both genuine affection and an awareness of how easily the complicated man could be replaced by the comfortable icon. When Einstein died in April 1955, the physics community's settled view of the Bohr-Einstein debate was clear and almost unanimous. Bohr had won. Einstein had lost. The argument was over. That verdict was not unreasonable given the evidence available in 1955. quantum mechanics had produced 30 years of results of extraordinary precision. Every experimental test it had faced, it had passed. Bohr's Copenhagen interpretation, whatever its philosophical difficulties, had proven operationally adequate. It told physicists what to calculate, how to calculate it, and what results to expect. Einstein's insistence that the theory was incomplete had not produced a single concrete result suggesting what the missing piece might look like. His unified field theory program had generated no testable predictions. His objections to quantum mechanics had been answered, at least formally, by Bohr at every turn. The younger generation of physicists had grown up treating the Copenhagen interpretation as settled background rather than active debate. To question it was not exactly forbidden, but it was regarded as a sign that one had not fully understood the theory, a philosophical confusion masquerading as a physics problem. Einstein's position had been absorbed into the category of brilliant man past his prime, understandable as biography, irrelevant as physics. Then, in 1964, John Stuart Bell published a paper that changed the terms of the argument permanently. Bell was 34 years old, working as a particle physicist at CERN in Geneva. He had been thinking privately about the EPR paper and about David Bohm's pilot wave theory for years, in the margins of his actual research. He was, by his own account, troubled by the dismissiveness with which the physics community had treated Einstein's challenge, not because he was certain Einstein was right, but because the dismissal seemed to him to rest on assertion rather than demonstration. The assertion was this: no hidden variable theory, no theory that assigned definite properties to quantum systems independent of measurement, could reproduce all the predictions of quantum mechanics. This claim had been stated by John von Neumann in a 1932 proof that was widely cited as establishing the impossibility of hidden variable theories. Bohm's 1952 paper had already demonstrated that von Neumann's proof contained an assumption that was not physically justified. That Bohm's pilot wave theory was a functioning counterexample to the alleged impossibility, but the physics community had largely declined to engage with this demonstration seriously. Bell went further. He did not just show that hidden variable theories were possible. He derived a mathematical condition, an inequality, that any local hidden variable theory must satisfy regardless of its specific details. The derivation was elegant and relatively simple. It rested on a single physical assumption, that the properties of a particle in one location cannot be instantaneously affected by what is done to a particle at a distant location. This was Einstein's locality condition, the core of what he had called local realism. Bell showed that if this condition held, then the correlations between measurements on entangled particles, the kind of particles described in the EPR paper, could not exceed a certain limit. The limit was expressed as an inequality involving the statistical correlations between different measurement choices. Quantum mechanics, Bell demonstrated, predicted correlations that violated this inequality. The two theories, local realism and quantum mechanics, made different distinguishable predictions. The disagreement was not philosophical, it was mathematical and, in principle, experimental. The significance of this was enormous. For nearly 30 years, the Bohr-Einstein debate had been treated as a philosophical dispute that could not be resolved by experiment, a disagreement about the interpretation of a mathematical framework that both sides accepted. Bell had shown that it could be resolved by experiment. The question of whether nature respected Einstein's locality condition was an empirical question, not a philosophical one. The first serious experimental tests of Bell's inequalities were conducted in the early 1970s by Stuart Friedman and John Clauser at the University of California, Berkeley. Their results favoured quantum mechanics over local realism, but the experimental design had what physicists called loopholes, technical limitations that left room for alternative explanations. The results were suggestive, but not conclusive. The decisive experiments came from Paris. Alain Aspect and his colleagues at the Institut d'Optique conducted a series of experiments between 1980 and 1982, using pairs of entangled photons and measurement settings that could be changed rapidly while the photons were in flight, a design that closed the most significant loophole in the earlier experiments. Their results violated Bell's inequalities by amounts consistent with quantum mechanical predictions and inconsistent with any local realistic theory. The violation was not marginal, it was clear and reproducible across multiple experimental configurations. Local realism was experimentally ruled out. The meaning of this result requires careful unpacking because it is frequently misrepresented in both directions. What the experiments established was that Einstein's intuition about locality, his insistence that the properties of a distant particle could not be instantaneously affected by a measurement made here, was wrong. The correlations between entangled particles are stronger than any locally realistic theory can produce. Whatever is happening when entangled particles are measured, it cannot be explained by properties they carried away from the interaction point. Something genuinely non-local is occurring. What the experiments did not establish was that quantum mechanics is complete in the sense Einstein denied, that there is nothing underneath the probability wave, no deeper description of individual quantum events. They ruled out local hidden variables. They did not rule out non-local hidden variables. Bohm's pilot wave theory, which is non-local, remains consistent with the experimental results. The interpretation question, what quantum mechanics is actually describing, was not settled by Aspect's experiments, even though the experiments are sometimes presented as if they settled it. This distinction matters for the Bohr-Einstein debate specifically. Bohr won on locality. Einstein was wrong that nature must be local in the sense he required. But Einstein was right that entanglement was a genuine physical phenomenon, and not a philosophical confusion about the meaning of quantum mechanics. He was right that the correlations described in the EPR paper were real and required explanation. He was right that the explanation could not be a purely local one. He drew the wrong conclusion from these correct observations. He concluded that quantum mechanics must be incomplete, when the actual situation was that nature itself violated the locality condition he had taken as inviolable. The story of who was right and who was wrong is therefore considerably more tangled than the standard narrative of Bohr winning the debate suggests. Bohr's framework survived. Einstein's specific objections were answered, but the phenomena Einstein identified, entanglement, non-local correlations, the inadequacy of any purely local description of quantum systems, turned out to be exactly as real and as significant as he had insisted. The technological consequences began to become apparent in the 1980s and have accelerated since. Quantum cryptography uses entanglement to create communication channels whose security is guaranteed by the laws of physics rather than by the computational difficulty of breaking a code. Quantum computing uses entangled states to perform certain calculations exponentially faster than any classical computer can. Quantum teleportation, the transfer of quantum states between distant locations using entanglement as a resource, has been demonstrated experimentally across distances of over 1,000 kilometers. None of these technologies operate on the theoretical foundations Einstein was trying to build. They operate on the quantum mechanical framework he spent 30 years opposing. The entanglement they exploit is the same non-locality he found troubling and insisted must have a deeper explanation. He was wrong about the explanation. He was precisely right about the phenomenon. John Bell, who died in 1990 before the most recent and decisive experimental tests of his inequalities were conducted, was asked in a late interview what he thought Einstein would have made of the experimental results. Bell said he thought Einstein would have been very troubled. Einstein had hoped that the non-local correlations would turn out to have a local explanation, that the EPR argument would point toward a completion of quantum mechanics rather than a confirmation of its non-locality. The experiments said they did not, but Bell also said something else. He said he thought Einstein's insistence on taking the EPR argument seriously, on refusing to dismiss it as a philosophical confusion, on treating the question of what quantum mechanics was actually describing as a genuine physics problem, had been correct. The community had been wrong to dismiss it. The question Einstein was asking had turned out to be exactly the right question, even if Einstein's own answer to it had been wrong. Niels Bohr died in November 1962, 2 years before Bell's paper appeared. He never had to engage with Bell's theorem or with the experimental tests that followed. He had answered every argument Einstein had put to him at Solvay in 1927, at the Sixth Solvay Conference in 1930, in the Physical Review in 1935, and in subsequent exchanges until Einstein's death. He had answered them all within the framework of complementarity, maintaining throughout that the questions Einstein was asking could not be answered because they were not physically meaningful. Bell showed that at least one of those questions, whether nature is locally realistic, was physically meaningful in the most precise possible sense. It had a definite experimental answer. The answer was no. Bohr's framework survived the answer. But the question it was unable to ask had turned out to be the most important one. Princeton Hospital, April 18th, 1955, 1:15 in the morning. We are back where we started. The nurse on the night shift heard words in German, and then silence. By the time she reached the bed, it was over. The aortic aneurysm had ruptured. Einstein had refused surgery twice, once in 1948, when the aneurysm was first diagnosed, and again when he was admitted to the hospital 5 days before his death. His reasoning, reported by those present, was straightforward. He had lived his life. Prolonging it artificially, with no certainty of recovering the capacity to work, was not something he wanted. He said it was tasteless to prolong life artificially. He wanted to go when he was ready to go. He was 76 years old. Hans Albert had arrived from California and was present in the final days. Helen Dukas was there. The equations he had asked to be brought from Mercer Street were on the nightstand. The last pages of his unified field theory work, still incomplete, still unresolved, sat beside the bed of the man who had begun thinking about the structure of the universe in Aarau in 1895 and had not stopped for 60 years. What happened in the hours immediately following his death is one of the more disturbing episodes in the history of science, and it has received less sustained attention than it deserves. Thomas Harvey was the pathologist on duty at Princeton Hospital that night. He conducted the autopsy. In the course of the autopsy, he removed Einstein's brain. He did not have the consent of Einstein's family to do this. He did not have authorization from the hospital administration in any clear form. He simply removed the brain, placed it in a container of formaldehyde, and took it with him. Einstein had left explicit instructions that his body be cremated and his ashes scattered in an undisclosed location, a deliberate measure to prevent exactly the kind of veneration of physical remains that he had always found distasteful. His family carried out those instructions. His ashes were scattered in the Delaware River. The location was not disclosed, but the brain was not cremated with the body. Harvey had it. and Harvey kept it for the next 43 years. The story of Einstein's brain after 1955 is simultaneously bizarre, sad, and revealing about the cultural machinery that transforms a human being into an icon. Harvey was not a malicious man by any account. He appears to have genuinely believed that preserving the brain for scientific study was justified by its potential importance, that understanding what made Einstein's brain physically different from others would yield insights into the nature of genius. He sectioned parts of it, photographed it, and distributed samples to various researchers over the following decades. The research produced almost nothing of substance. Several studies claimed to find anatomical differences in specific regions of the brain, variations in the parietal lobe, differences in the density of certain cell types. But none of these findings proved robust enough to establish a causal connection between brain structure and the specific cognitive capacities that made Einstein who he was. The premise of the project, that genius has an identifiable neurological substrate that can be found and described, has not been supported by anything the study of Einstein's brain produced. What the episode revealed was something different and more interesting. The compulsion to reduce Einstein to a physical object, to locate his genius in a measurable, containable thing, was a response to the discomfort produced by the actual complexity of his life and work. An icon is easier to manage than a man. A brain in a jar is easier to study than a career spanning 60 years of physics, philosophy, politics, and moral reckoning. The theft of the brain was, in a sense, the most literal possible expression of the broader cultural project of replacing the real Einstein with something more convenient. Harvey eventually returned the remaining portions of the brain to Princeton Hospital in 1998, 43 years after the autopsy. He was 84 years old. He had carried Einstein's brain across the country in a cider box at one point during the intervening decades, transporting it in his car during a road trip that a journalist documented in a book published in 1995. The image of Einstein's brain travelling across America in a cider box in the trunk of an old Buick is not without a certain dark comedy. It is also, in its way, an accurate portrait of what celebrity does to the people it has consumed. The myth, meanwhile, had been assembling itself since before the body was cold. The famous photograph, the one taken on Einstein's 72nd birthday in March 1951 by the United Press photographer Arthur Sasse, had been circulating for 4 years. Einstein, tired of being asked to smile for cameras at a birthday party, had stuck out his tongue. Sasse captured it. Einstein liked the photograph and requested copies. It became one of the most reproduced images in the history of photography. It was exactly what the myth required: the genius as playful, eccentric, approachable, human, charming, the wild hair, the kind eyes, the tongue. The photograph did not lie exactly. Einstein was capable of playfulness and warmth, but it captured one moment from a life of enormous complexity and allowed that moment to stand in for the whole. That is what icons do. They select. The selection had been underway for years before 1955, the process by which Einstein's actual positions were smoothed into quotable wisdom, by which his specific, contested, sometimes wrong arguments were transformed into generic pronouncements about imagination and curiosity and the importance of asking questions, accelerated after his death and has never stopped. Calendars, motivational posters, corporate presentations, graduation speeches, Einstein's name and face have been attached to sentiments he never expressed, arguments he never made, and positions that would in some cases have struck him as absurd. He had said, clearly and repeatedly, that he did not want to be idolized. He had declined honorary degrees from institutions he found politically objectionable. He had refused the Israeli presidency. He had asked to be cremated without ceremony. He had said, in as many ways as a person can say something, that the icon was not him, and that the icon was not useful. None of it worked. The icon was more convenient than the man, and convenience tends to win. What the icon discarded is the substance of this documentary. The patent clerk working in the margins of his official duties, the man whose relationship with Mileva Maric raises questions that have never been fully resolved, the father who did not see his younger son after 1933, the physicist who helped launch the quantum revolution and spent 30 years arguing it was incomplete, the man who signed a letter that contributed to the most destructive weapons program in history and spent the rest of his life doing penance that could not undo what the weapons had done, the scientist whose most dismissed paper, the EPR paper of 1935, contained the seed of quantum information science, the old man working on equations he knew he would not finish, declining surgery, asking for his papers, dying at 1:15 in the morning with German words on his lips that no one present could understand. The autopsy photographs were published without the family's consent. The brain was taken without the family's consent. The image was reproduced billions of times without Einstein's consent, attached to words he never said, in service of ideas he never held. The pattern holds. The man's wishes regarding his own legacy were simply set aside in favour of what other people needed him to be. If this kind of documentary, built on research, committed to complexity, unwilling to trade accuracy for comfort, is the kind you want to see more of, then subscribe. Leave a comment about which part of this story surprised you most, and share it with someone who still thinks they already know who Albert Einstein was.